I know.
Introduce our first speaker for the day. It is Professor Francesco Chiodi. Sorry, let me just check. They should be able to hear us online. Yes. Okay, so our first speaker today, Prof. Francesco, sorry, Prof. He is a professor in quantum computing here at Stellenbosch and also the director of Mythics. Prof, privileged to hear from you.
Thank you.
Thank you.
Thank you very much. Yeah, good morning, everyone. Thank you for the invitation to speak, and I'm sorry that I missed the first 2 days of the conference, and I will miss the rest of the day as well. Yeah, it's the end of the year is always a very busy period. Yeah, as Sibu certainly knows. Yeah. Okay, since this workshop is about dynamical systems theory, modeling, and AI. I tried to offer a talk that has a little bit of every element. Yeah, and it's recent work done mainly with 2 PhD students. Yeah. Can I remove this? Yeah, no, I just wanted to remove the view of all the people because otherwise I can't see my slides. Yeah? So the idea is to automate the designs of architectures for machine learning. Yeah, using typical tools from theoretical many particle physics. Yeah, so essentially, what one tries to do is to let the machine do better than humans, yeah, and optimizing architectures for neural networks. Yeah? So I will start with some background and motivation, then I will show you the technology, and at the end give some applications. Yeah? And mainly this is the work of Matt, PhD students, and the last part of Amy, who is also a PhD student in Stellenbosch, and a few other people that contributed a little bit here and there. So let's start with the background and motivation. Yeah? Oh, okay. Sorry, there's a little bit of a delay. Until around 2012, yeah, and that is the title, the cover of a typical machine learning book of that the time. Yeah. All machine learning models, you had sort of to build in features more or less by hand. Yeah? So there was lots of kind of background knowledge that went into your machine learning algorithms. Yeah? The big revolution started in around 2012, and this is one of the famous papers of the time, when with deep learning, the neural architecture started learning the features on their own. Yes, there was no need anymore for fiddling around manually. Yeah, and that kickstarted also the area of neural architecture search, of finding somehow automatically the optimal architecture to solve specific problems. And the whole idea of the talk is to show how some of the ideas from classical machine learning can be converted to quantum machine learning with some profit. Yeah. So the basic idea of the neural architecture search is, of course, you start with defining some search space. You need a strategy. You try an architecture. You have some estimation of how good your architecture is, and you do a little loop until it sort of converges. Yeah, and you know that has been done classically many times. Yeah. Essentially, the problem is, you know, the classical problem, yeah, is that each node there corresponds to some layer in a neural network. Yeah, that could be a convolutional thing, a pooling thing, and so on. But but the architecture is sort of fixed. Yeah, so it's quite difficult to improve on something that it fixed. Yeah? So the idea is that to adopt kind of hierarchical strategies, yeah, where you start with defining kind of primitive elements of neural networks, and with kind of evolutionary strategies, you put them together for your optimal purposes. Yeah, that's what we want to do. Yeah. So typically, you have something like that. You define your kind of elementary primitives, building blocks of your neural network. You put them together in a kind of a hierarchical fashion, and you try to convert it then in the same idea in quantum language, if you want. So how does this automated design work? As I mentioned, the basic idea is to use tools that have been known for a long time in theoretical quantum many particle physics, and essentially the tensor network model. Yeah, you can have like under a typical generic tensor network, but for many practical uses, people like maybe more linear structure, like these matrix product states, yeah, in B, or the PEPs, the projective entangled pair states, or more hierarchical kind of fractal tree-like structure of another one, E, that is very popular, this multi-scale renormalization answers called also MERA. Yeah? And these really allow to develop this hierarchical representation that will be very, very important for the following. Yeah? For instance, just to show you that there's a natural match between these tensor network structures and the neural network. If you translate the typical classical convolutional neural network structure to a quantum algorithm in the block in the middle, essentially, yeah, you can see, comparing with the block at the bottom, that it's essentially the Amera structure upside down. Yeah, so you can really match very nicely hierarchical or convolutional neural network architectures into this tensor network language. Yeah, let me show you how these primitives looks like. Yeah, if you have, for instance, these eight nodes and a step one, all one connected to the nearest neighbor, you can map it easily to a primitive building block of a quantum circuit. Yeah, the 0, 1, 2, 3 are your input state, and the other symbol indicate which qubit interact, for instance, with a CNOT gate or something like that. Yeah, you can have also other primitives that here where only two qubits are connected, your pairwise. That would be a kind of a step 2 kind of geometry. And then the idea is that this building block, you put them together, yeah, to create more complex quantum neural network or quantum circuits. For instance, in this configuration where you have a mix of the step 1 and the step 2 neural networks, primitives. Yeah. Once you have defined the primitives and you put them together, you then apply evolutionary strategies to optimize your network. Yeah, you start in A by defining your primitives, then you can compose them. You need, of course, to initialize your circuit, apply your evolutionary search, and sometimes if you have symmetry in the system, the evolutionary search breaks it, and you have to fix it, yeah, and keep going until you reach exactly what you want, yeah. And this is essentially the basic idea. Let me show you maybe now the application and see that it actually works. Yeah? In statistical physics, there are some standard models like the LMG model, or a variant of the Ising model, where the task is to find the ground state. Yeah? So these are fairly simple Hamiltonians. Yeah? And if you apply this whole machinery, yeah, you see, for instance, something very interesting that sort of caught us by surprise, because it not only gives you efficient quantum machine learning circuits, yeah, but it also opens up the way for new analytical approximations. Yeah? If you look at the circuit that the evolutionary algorithm learned, you can interpret it very nicely as a first layer that corresponds to a very basic mean field approximation, yeah, plus correction terms, yeah, that are different from what you would have done normally, yeah. So it's really very interesting because it connects the computing with analytical tools as well to go systematically beyond the mean field approximation. Now, this was a very nice surprise that we were not expecting at all. Yeah? And you can see it here. Yeah, if you try to find now apply to the LMG model, yeah, and you see increasing the number of spins in your chains, you can reproduce very nicely the exact solution for every almost arbitrary number of n, and even in the limit for n goes to infinity, the approximation is really spot on. Yeah, so this is very nice. Yeah, you can look at the errors; these are also very, very nice. And but maybe, and here you see nicely that we have a nice approximation. Yeah, because here this is a correlation function for the Ising model. Yeah. The density function for the Ising model, yeah, and again you see for increasing the number of nodes in your chain, it works very nice, yeah. But in the limit n to infinity, yeah, we are much better than the mean field approximation. You see, the mean field approximation is the dotted line there. Yeah? Our ansatz is much closer to the expected exact solution. Yeah? For some reason, it doesn't get it perfectly. Yeah? But you know, there might be ways to fix it, yeah? Or to make it a little bit better. Yeah? But anyway, it's also really a systematic approximation beyond mean field that seems to work much better than mean field. Yeah. Another aspect that is very nice is that the ansatz is very robust. Yeah. If you change your initial configuration and you disturb the system a little bit, again and again, it comes up with the same optimal solution. Yeah. So it's really that is really very nice. Yeah. Another application where the power of this really comes out is looking at phase transitions. Yeah. And this is, again, another variant of the Ising model with a known phase transition. Yeah. And here we compared our results on the right with previous results on the left, where people also with convolutional neural networks try to identify the borders of the phase transition. And you see that it works really very well, much better. But it gets even better because if you look, and here's just the circuit that comes out of the evolutionary procedure. Yeah, if you look on the table on the right, yeah, and the number of parameters, yeah, the original work, yeah, had 1,300 parameters that you had to optimize in your variational circuit. Yeah, with our approach, you boil it down to 11. Yeah, which it's a significant improvement in performance. Yeah? So that's really very nice. Now comes the sort of almost semi-magic part, yeah, because now you can use the same strategy to invent algorithms. Yeah, you train your convolutional neural network and you try to let him invent quantum algorithms. Yeah. So far, we were only able to reproduce known algorithms. Yeah, for instance, you can train your system. This is just an example, and it rediscovers the Deutsch-Josse algorithm, yeah, which is one of the standard basic example of quantum computing. Yeah, it can also reinvent Grover. Yeah, it finds it quite nationally. Grover is a standard search algorithms on quantum computers. Yeah? And you can also find the algorithm for the quantum Fourier transform and for many others. Unfortunately, we haven't found yet a new one. Yeah, but hopefully it will happen one day. Yeah, not in the too distant future. Historically, we started doing this. Yeah, when we started looking into quantum version of convolutional neural network, we wanted to see whether it allows you to, for instance, to classify music genres. Yeah? And this was our very first attempt. Yeah? You take time series that correspond, say, to classical music, rock music, country music, and so on and so forth. You do your whole neural network optimization procedure, and it turns out that you can really improve on other convolutional neural network approaches. Yeah? So you see the red is what comes out, the success rate, say, of our classification compared to other convolutional strategy. Yeah, so that was very nice. Yeah, and one of the things that we want to do now, and I mention it because Fatima is sitting here, yeah, is to see if we can use the same approaches also to investigate more medical kind of time series like EEGs or other things, and hopefully it will work well there as well. Yeah. So coming, sorry, I think I rushed a little bit too much. Yeah, but maybe you have time for questions. Yeah. So just summarizing, it's very important to, if you want to optimize the architecture of quantum circuit for complex neural network, to start by looking into primitive building blocks. You put them together hierarchically, and with evolutionary strategy, you optimize the feature of your algorithm. Yeah, and so far we were able to show that it works very nicely if you want to find ground states of thin systems or identify quantum phase transitions and so on and so forth. Yeah, and hopefully it will lead even to other useful things. Yeah, so I think we have enough time for a few questions. Thank you very much.
Thank you so much, Prof. Shall we first see if there's any questions from the online? No, Sergey. Sergey not busy today. Okay, then we'll see if there's any questions from the audience.
If we are start a new research for the deep learning, machine learning, so which are the basic book for how to learn the machine learning, the basic book for the machine learning?
For classical machine learning, there are probably millions of books these days on classical machine learning.
I ask you, any prefer book means
you need
first you are starting, suppose you are a new researcher.
There is that standard deep learning book by Benjo and others that is probably still a good starting point. Okay. Yeah, probably, but there are many. Yeah.
Any other questions from the audience? Yeah, it's Shane.
Thanks, Francesco. I'm very curious about the evolutionary search for the architecture. How important is that? Is it possible to do some kind of gradient-based optimization, or is the process non-differentiable?
We wanted to avoid the gradient-based.
Can you tell us a little bit more about why?
Yeah. Because this turned out to work much better. Yeah.
Okay. Yeah. Okay. So there's no specific.
No. It just we tried, but they evolutionally turned to help much better in this kind of application.
And is it possible to do this kind of search within a Bayesian framework? In a Bayesian framework.
Probably. Yeah. I don't know. We didn't try, but probably. Yeah. I don't know. We can just look into that. I don't know. We didn't try that. Yeah. We didn't even think about it.
Any other questions? I want Prof to not go over time, and he took me very seriously. Thank you so much. Another upload.
Pleasure. Sorry. Here we go. Sorry. What the next speaker?
Put this on my. I see that.
Yeah.
Okay, so I just want to check, is that?
Mute.
Yeah. Our second speaker for the day is Dr. Shane Josias. He's a lecturer here in applied mathematics at Stellenbosch. Thank you, Shane.
Thanks, Emma. Morning, everyone. Just want to check. I assume everyone can hear me online, but the folks at the back will tell me whether that's not true. Today, I'm going to discuss this idea of generative modeling, and specifically how we can use differential equations as a framework to make this possible. Of course, there'll be a little bit of detail in this slide, hopefully not too much. I'll try and just go over the high-level details. And then maybe towards the end, I'll discuss a more specific research question that came up while I was doing my PhD on this topic. So, of course, this is a workshop on dynamical systems, and today is the AI machine learning day. It turns out in recent times, in the last few years, there's been quite a bit of overlap between machine learning and differential equations. Right? So one could, in principle, use machine learning to solve differential equations or to discover parameters for differential equations for a specific problem. That's not quite what this talk is about. Instead, what we're going to do is to think about how differential equations can serve as a computational framework to solve the problem of generative modeling. Great. So to start, I'm just going to sort of at a high level discuss that more than just generative modeling, neural networks or dynamical systems can be used to understand machine learning, right? And when we think about deep learning, we're typically thinking about modern neural networks. For the purposes of today's talk, we should think of this as a parameterized function with many, many, many parameters. And depending on what task we're interested in, we want to find values for those parameters through some kind of optimization problem. Right? And so if you think about initializing the parameters for this model, this function, and learning those parameters through optimization, they evolve over time. Right? And so one way that differential equations has been used in machine learning is to model the evolution of parameters during training, to understand convergence, to local optima, and also to design new algorithms. Right? But again, as I said, we're thinking about using differential equations as a computational framework, and specifically for generative models. So for the next few slides, I'm just going to discuss this idea of generative modeling before we bring the differential equations back into the picture. Okay, so we're quite familiar with a generative model. I think this is now the classic example, ChatGPT. Many of us use ChatGPT. It's an example of a large language model that we can interface with through text. Right? So you might decide to ask it, hey, chat, what are deep generative models? And it will give you an answer which I happen to think is quite sensible. How does it do this? Well, conditioned on this prompt that someone, not me, gave it, it generates a sequence of text or a sequence of characters that are more likely than other sequences of characters. And that's the main idea, right? Is that if I asked what are deep generative models, I better not get a recipe for a cake, right? So those sequence of characters would be less likely. And actually, if we think about this in a little bit more detail, and you read the last sentence, that we can think of generative models as, and I'll quote here, they learn the underlying distribution of the data and use this knowledge to create new instances that are similar to the original data, but not identical to any specific training exact, and it kind of cuts off them. Right, so we can think about the possibilities here. It could be exact, it could be examination, it could be exacerbate. Those are all possibilities for the completion, but maybe the most likely possibility is examples, right? Because that's what we feed the model during training, examples. And that's the idea. We can extend this to more than one type of data. We could do text and text to image generation. In this case, you might wish to ask your model to generate an image of a teddy bear teaching a course with generative models written on the blackboard. And then we get this really quite cute and pretty picture of a teddy bear standing on a desk in some kind of classroom setup. Again, here we're now, instead of generating text, we're generating pixels. And some arrangement of pixels should be more likely than others. Right? Generative models encodes this idea of likelihoods that we can then use to generate new data that in some way is sensible with the text. Specifically for this image, you'll notice that the text is quite good. I think maybe 2 or 3 years ago, this was a difficult problem getting coherent text, but we've made quite a bit of advancement towards that. These examples are nice and they're good to look at, but generative models also have applications in science. For instance, if we're thinking of doing precipitation nowcasting, which is the problem of predicting in some way the sort of level of precipitation or rainfall up to 2 minutes ahead of time, right? And so you've got maybe have some observations of rainfall. Of course, there'd be some ground truth at time t. And if you were to, in your training set, observe a distribution of rainfall 30 minutes later, 60 minutes later, and 90 minutes later, perhaps you'd wish to train a generative model that would in some way give you that same kind of rainfall map. And so generative models have been used in this case as well. And so we've got interesting applications for large language models, which have really helped us become more efficient at our jobs, hopefully, but there's also applications in science, right? But of course, we're going to try and think about how to construct a generative model within the framework of a differential equation. Great, so let's formalize things a little bit more. Let's say we're interested in modeling data, right? That's the name of the game. So we're going to start with a very simple data set. Over on the right, we've got a collection of 2-dimensional samples. You'll notice there's a bit of structure. There seems to be 3 modes in the data set, and each of those 3 groups of data has a certain shape. Right? The middle one's a little bit more round, the bottom one's a bit elongated. So I could say, well, I'm going to model this probabilistically with a function that will look something like this. I've got 3 terms in this function for each of the 3 modes, and they are all Gaussian because, in fact, they do look Gaussian to me. The Gaussian will have a parameter mu saying where it's located and sigma k, right? So there's parameters to the model. This is good. And if I were to be able to estimate the parameters in some way, we could do 2 very important things. One is to generate new samples that look like the data. Right? So I would get samples that kind of look like this, but not samples that are in that region. But I have a density function for the data, which exactly tells me whether a sample is highly likely under the model or whether a sample has low likelihood. And so you could think of this as some kind of heat map over the space, encoding regions of space that are more likely. And this is typically quite good if you want to do something like outlier detection. Right? For so many of the examples that we looked at, specifically images, that is my area of research. we have to estimate this function from high dimensional image samples. Right? That's the important part here. And this is a tough problem, right? And where differential equations come in is to construct a continuous time normalizing flow. Right? And that's what we're going to. Okay, great. What is this? Well, the idea is that you would typically have data, right? We've got samples, and we can define a closed form expression for some type of noise distribution, like a Gaussian or a standard Gaussian more specifically. Those are the two givens, the two knowns, and we want to model the probability distribution over the data through some kind of invertible transformation, right? Between samples from the data and samples from the space distribution or source distribution. Right? How can we do that? Well, we can treat this as an initial value problem, right? Where there's some kind of continuous time transformation between samples from the base or the source distribution and the target distribution, and there's sort of dynamics specified by a neural network with parameters theta. Right? So at time t0, you've got the noise, and at time t1, you'd have the data. Right? So this is what a continuous time normalizing flow is, and it turns out there's a continuous analog for the change of variables formula that gives us an exact quantity for the log likelihood of the data. So this is quite helpful. What we would do at this stage is to solve both of these equations. Right? Solving these equations will give us either depending on which direction you go, a data point or a sample from the base distribution, but it would also give you the likelihood. And once you have the likelihood, you can solve or do maximum likelihood training to optimize the parameters for this neural network. Right? And this is the framework. Quick example. Let's see if this shows. Okay, we'll work with this for sure. We can again think of a two-dimensional example. On the left, you'll see samples being transformed continuously from this space distribution, which would be a Gaussian in this case, to the intertwining moons, two-dimensional data set. In the middle, you have the dynamics function, which is time-dependent. And on the right, we have that transformation of log probability, again, from the base to the distribution. And of course, we would have to solve these two equations, which happens to be quite computationally expensive. We've got high-dimensional images, right? So our inputs are high-dimensional. We're doing a continuous time transformation. So our dynamics are also in high dimensions. And so this happens to be quite expensive. We also have to estimate the trace of the Jacobian. And even though there are statistical ways to do this, this is still quite expensive. And of course, it's expensive because of the need for an ODE solver. Right? So we use an adaptive solver to solve these systems. And the solver may require more function evaluations in regions where there is greater curvature. And so maybe there are some research questions here that one could have in terms of how do you regularize the dynamics function, which is your neural network, to avoid this case where they're prohibitively expensive to train or prohibitively expensive to sample. Of course, maybe there are more opportunities here to also think about how we should adapt our solvers for this specific problem. Is there stiffness in the system? Should we be using implicit solvers? And so I think there are some opportunities there for research. But of course, the community it's always this trajectory of coming up with an idea, realizing there are some challenges like the scalability, and then coming up with creative ways to solve that. And it turns out to train these models, you don't in fact even need to simulate solution trajectories. Instead, you could use what we know as flow matching. Right? And so the idea with flow matching as a scalable way to train these models is to think about the evolution of probability as what we'll call probability paths. Right? And so there's a function, PT, which tells us how the probability, log probability evolves from time 0 to the eventual time 1. Right? And the vector field or dynamics, there's some ut that would induce this probability path. And these two are related through the continuity equation, right, over here. So which means we can think of this as a transport problem, right? And of course, there's quite a lot of mathematics involved, but this leads to a neat training objective where all you need to do is regress your neural network vector field against this target vector field, right? And that's the objective that we solve. Instead of simulating many trajectories, doing maximum likelihood training, we can now instead just regress it against some kind of target. This target happens to be unknown. It's not possible. And so we simplify the problem by considering a conditional probability path. And this is a path from some kind of Gaussian-based density to a density concentrated around a single data point. All right, and so if you define this conditional probability path, there happens to be a closed form conditional vector field that induces this probability path, leading to a much more simplified training objective where we now regress that vector field against this new target. And we'll see some specific forms for this a little bit later. But perhaps what I'll say here is that this conditional path gives us a density from this Gaussian base to a single data point, but in expectation, this converges to the global vector field that would transport an arbitrary data point to the data distribution, or the log probability to the data distribution. And that's the general idea. We can simplify training by quite a lot to give us access to this vector field, which is our continuous normalizing flow. Great. So we now have a continuous normalizing flow generative model, right? And we have a scalable way to train it through flow matching, conditional flow matching. These have been extended again to high resolution image synthesis. That's always the classic benchmark for many models in machine learning. How good can you classify images, and how good can you generate images? Again, because it's this high dimensional problem, that's quite difficult. But again, there's applications in science, for instance, protein generation, which is quite helpful for designing drugs from scratch, instead of the typical way of designing drugs through lab experiments. Of course, I know absolutely nothing about protein design, but I'm sure the authors of that paper would have more details. Great. So that's, again, the general setting. We're trying to generate images in this talk. There's an expressive model to do this. Expressive, again, because the problem is quite difficult. For my PhD, I looked into some of these models. Of course, I trained many of them, but I was quite interested in the ability to get exact likelihoods on these models, right? So these normalizing flow models will give us exact likelihood evaluation. This isn't true for all generative models. Some generative models model the sampling process. So you can sample new data, but you can't evaluate likelihoods. Other generative models can give you a lower bound on the likelihood, but normalizing flows and continuous normalizing flows, as we've looked at, give you exact likelihoods, right? And so this is an advantage. And now we have a computationally efficient way to do that. Well, there's an interesting problem in that trained models would assign higher likelihoods to out of distribution data. And what do I mean by that? If I train a model on images of fashion items, we would expect the model to give high likelihood for new samples from that data set, and this is true. But as it turns out, there's another data set for which the model would give even higher likelihoods. And it's quite obvious that, well, even though there are some similarities between these data sets, numbers in its structure is quite different from fashion items. And so we think of this data set as out of distribution. Yeah, I don't know if you might need to use the mic. Yeah.
The phrase is bothering me. in a sense that it's either likelihood with certain probability or not. Exact means what? Probability 1?
Oh, no. We're not thinking about exact as probability. So we can think of a likelihood in some sense as a probability. It's not quite a probability, but we can think of it as the model's belief of how likely it is a sample would come from the data, but that likelihood is a number, right? And what I mean by exact is that some models don't give you this number. Other models give you a lower bound on this number, but this framework gives you that number exactly. Right? So like we can think of likelihood as a number between, or let's just think of it a number to simplify things. This framework gives you that number exactly. Of course, we're solving ODEs here to get it, so there's some numerical error. You won't get it exactly, but theoretically, the framework gives you an exact number. Is that better? Okay, we can certainly chat afterwards. Yeah, and maybe we should continue the discussion at the end. Okay, great. So of course, there's this one example of the data set. There's another data set for which this is 2. That's the C410. If you train a model on C410, you would get even higher likelihoods on SVH. Right? And so this is undesirable. We were promised exact likelihoods, and maybe some of us in the audience are a little bit uncomfortable with that term. But this is what we were promised. We don't get that. Of course, if you're doing outlier detection, you certainly don't want your model to say that an outlier is in distribution, right? And so this is the idea. Okay, so we have a scalable way to train them, but we have these unreliable likelihoods. One of the research questions that I looked at is well, are there ways to parameterize that base distribution in the transformation that could then lead to reliable likelihoods? So I've spoken about a base distribution as a standard Gaussian, but we're not restricted to this. There's some flexibility there. Can we think about other forms for that base distribution? Does that help us at all? All right, so our log likelihood term gets decomposed into these 2 terms. We have a log likelihood under the base distribution and in this Jacobian term. And if you were to plot the histograms for log likelihoods under the base, you'll notice the same kind of out of distribution data behavior. So over there, I plotted the log likelihood histograms, which gives us the number of likelihoods at a specific level on the x-axis. And you'll notice that on average, the out of distribution data gets higher likelihoods because it's on the right of the blue in distribution data. Right, and so maybe there is something going on in the base distribution. Can we do a different parameterization? And we look into whether having a multimodal base distribution would help. And just to get some intuition, if we take this 2-dimensional moons data set and a black point over there, transform it to a unimodal base, we'll see that out of distribution black point gets transformed to a location of high likelihood under the base distribution. It's right in the center. Standard Gaussian has the highest likelihood there. But if we do a data-specific multimodal base, then we'll see that same black point gets transformed to a region of much lower likelihood. Right? And so we wanted to see if this observation would extend to the higher dimensional case for images. Great, so we've got a training data set. It's class labeled here because we're going to parameterize that base distribution in a class-specific way. We've got samples X and labels Y, and we define the initial condition as the data point in this case. We'll do the standard base, which is a standard Gaussian, and then we'll do a multimodal base distribution as a GMM, where each of the parameters are estimated from the class data. So μk would be the empirical class means, and we have some freedom in choosing sigma k. Right, and so we need to specify the target conditional vector field for each base distribution, and that would give us a training objective. Okay. Okay, so this is our objective. We're looking for forms for the conditional vector field. The standard base distribution looks something like this, where you have the data point there, and there should be some arbitrary a solution at some arbitrary time step in between the two times. Again, reminding everyone that there's a continuous transformation from a density from a standard Gaussian to a density concentrated around the data point. There's a similar expression for the GMM-based distribution. Now it's got an additional term for the class means, right? And this sigma min is chosen to typically to be very, very small. In practice, when we train these models, we have to sample Z0 from a base distribution. And so for the GMM, we sample it from the Gaussian component corresponding to that class. Right? And that's the main idea. These are the data sets that we've used. You've seen them in an earlier slide. MNIST, fashion MNIST each have 60,000 images, and the C410 and SVHN data set. What we're going to do is to train what I'll call a CFM model, right? A flow model or a continuous time normalizing flow trained through flow matching on using the standard and GMM based distributions, evaluate log likelihoods from these trained models on in and out of distribution data sets, and then maybe also have a look at the quality of generated samples. Do we have a generative model if we don't look at what it's generating? It turns out that sample quality and likelihood, let's call it fidelity, turns out to be independent, right? And so if you get good samples, you can't necessarily expect good likelihoods, but looking at the quality of generated samples can, in some sense, give us an indication of whether we've actually learned a generative model. Great. So I'll do one case. So we train a model on C410, evaluate it on SVHN as out of distribution. And when we look at the log likelihood plots again, you see that for the standard base, on average, the out of distribution orange bars have higher likelihoods than the in distribution set. So of course, this is the problem we're solving or trying to solve. But it turns out that parameterizing sort of class-specific information in the base distribution didn't help us either, right? And so that was a little bit of an unfortunate discovery. You still get much higher likelihoods, and maybe points to the idea that the base distribution might not be responsible, and there are other factors at play, right? And so we do see that does not lead to reliable likelihoods. We checked whether there was some alleviation of this problem under the base distribution, but this didn't turn out to be the same. It's still not quite likelihood, and the same holds for the other data sets. Of course, parameterizing the base distribution in this class-specific way does give you the ability to do class conditional sampling. I just sample from a specific Gaussian component and then do the generation process. So there are some advantages to doing this anyway. Right, the quite peculiar thing is that if you swap the two data sets around, so if you train on SVHN and evaluate on C410, you don't see this behavior. So at this stage, we're thinking that maybe there's something about the structure of the data instead that might lead to reliable or unreliable likelihoods. But at this point, there's no way to predict ahead of time whether models would be reliable or not. Just quickly look at sample quality. At the top, we've got the real samples for reference. In the middle row, you have samples drawn from the standard base distribution. And you'll notice that this C410 data set happens to be quite difficult, and some samples are not recognizable. Although if you look really closely, that's kind of a car, and that looks like an animal. I couldn't tell you which animal that is, but does look like that. Then this is for the GMM-based distribution. And the interesting thing to note here is that there are some classes that are repeated in this generation process. So in here, we've got a 7. Here, we've got many t-shirts. And so we seem to think that training these models leads to some kind of mode collapse. Great. And then before I end off, I'll just show a very quick qualitative experiment. we can think of using the Frechet inception distance as a way to evaluate the quality of generated samples. The idea is you take your generated samples and you compare the distribution to the distribution over features of a reference data set, and lower would be better. And the experiment here, qualitatively again, is to take the data. Of course, if you have a data set where all the images are left unchanged, it would have an FID close to 0 when compared to the original training set. But now what we'll do is to shuffle patches of these data sets. So you can shuffle 4 patches. And now you'll see that with the higher FID, we're going further away in distribution to the training set. And we can even do that with more patches, of course, destroying the images. And the FID here becomes much, much higher. If we look at its impact on the likelihood scores, we'll see that the likelihoods are changed to a much lesser degree. Right? And so this is quite an interesting observation. We jumbled up our pixels, and the models still believe that there's some kind of overlap in likelihoods for these samples. Again, indicated that maybe the problem lies in the structure of image data in high dimensions. And so we are looking into this idea of whether training on feature representations can help. Right? But that's more or less what I've been looking at in recent times. Okay, so let's conclude. We looked at continuous time normalizing flows, parameterized by an ordinary differential equation as an expressive framework for generative modeling of high dimensional, in this case, image data. Of course, not restricted to image data. There are some scientific problems that can be addressed as well. We looked at a very specific research question where models trained with this scalable objective gives you unreliable likelihoods and out of distribution image data. Played around with some multimodality in the base distribution, didn't help, unfortunately. But again, they do enable class conditional sampling. So there's some benefits to doing this space parameterization. We fix the parameters to the training data by computing the class means. But maybe we should think about learning the GMM parameters. And we all assumed access to class labels, but can we do this without class labels? And then we saw that models fit strongly to pixel level statistics. So maybe we should think about training on feature representations. I wonder as well whether other parameterizations of that vector field that gives you the transport from the base distribution to the GMM distribution can help. And then maybe we could think of the geometry of the transformation to see if there's any opportunities there to characterize this phenomenon of unreliable likelihoods in some way. So I think I'll end off there, and maybe we can discuss the exact likelihood question again, and also hear if there are any other questions.
Thank you, Shane. Almost doing my job for me. Let's first see if there's any questions online. None. All right, then we'll open to the audience. You go. Hold on, give me 1 second. All the way at the back.
Can you go to slide 17, I think?
17.
When you're doing the conditional matching flow, this one, yes. So you're moving the distribution to that peak distribution on the sample point there. Would it be true to say that like any linear vector field actually with that fixed point would do the job?
Yep, yeah. And in fact, to say so.
Like do we need
so
to train a model? Like I could
so the
take
question
any
is,
linear vector field.
Can you parameterize this as a linear vector field? And I think the important distinction to make here is that we might be able to do that for a specific sample, but in expectation, would that lead to the distribution over the data? So we have a conditional vector field that goes up to a specific data point. We have, of course, many options in a simple one like this, but the important one is that we want to choose forms for this that would, in expectation, give us the distribution over the data. And why that happens to be important is that the simplification of, I'm going to go even further back, this simplification here, this loss, has the same gradients as the more general formulation. And so when we optimize the parameters over that, we do actually guide the neural network through gradient descent to the global solution.
Okay, but I'm trying to understand what's special about the vector field that you get compared to a simple linear vector field that will push you to the same point.
I think it's maybe I'm not understanding your question.
It's something we can discuss
okay.
afterwards. But
Okay.
That's good.
Yeah.
Thanks.
I was actually wondering on that point, you wanted to focus on the white dot. Assume I'm not in machine learning, so give me some grace. But it seems to get bigger and smaller, or maybe more intense or less intense as it moves towards that dot.
Oh, yeah, that might just be a visualization
So it's not
quirk.
that
No,
because
so
yes.
we should expect the distribution to converge to a single point, right? Yeah, so we can think of it as a Dirac. Yeah.
Any other questions from the audience? Prof. Kara, do you want to revise your topic?
This question is not so much about what you're specifically doing in your methods, but pay attention. The reason I'm asking Andronikos to get involved, I get the feeling, if you have a minute or two, this is the kind of thing that was done in identifying black holes eventually, the picture of the first black hole. Because what we're feeding the system with is what something should look like, or what we think something should look like, and then we find it. And when I started thinking about how did they know that eventually the picture they got was the picture of the black hole and the world celebrated. So if it's a picture of a cat, we know what a cat looks like. So we search for it up there and say, it's a cat. But the black hole, I mean, there's a physicist here. The image we have of a black hole is based on equations and probable solutions and so on. And then we went out looking for the things that we think what something should look like. And the problem I have with that is, what if that is not what it should look like?
Sure. Of course, I've absolutely no idea what they did to generate that image of the black hole. But the important distinction is that, as you quite rightly point out, we don't have an image of a black hole. But for these models, we have training data, right? So we've got images of cats and we've got images of dogs, and so we do have a set of data that's representative. Of course, there is a question: do we have enough data? And that could be a problem as well. We can get much better models by getting more data, but there are distinct differences, I feel, between these two problem setups.
Although that moving picture did behave like a black hole, it got captured by that white hole.
Yeah. Okay. No, fair.
Yeah.
I'm just curious, but is there like a notion of, can I say, sensibility in, it's like, does it make sense that the output of that, how can I explain this? Because like what I think is that, because I don't know if this is true about like LLMs, but for like text, I think the probability of one word or phrase is dependent on what happened for the previous one. So the probabilities are dependent, they're not independent. And so now obviously based on what happens from the word before, you could end up running away down a route that is completely nonsensical. You'll have gibberish based on, or in terms of like not the intended outcome of what you wanted. So I'm just curious, is there like a notion of sensibility, or is the training set or data we feeding these models the way we try and create this idea of what is a sensible solution or output?
Yeah, that's an interesting question, because when we're thinking about generating text, we're thinking of a conditional density, right? So you want some probability over output condition on some inputs. We don't quite have that here. We parameterize some transformation between two spaces. Of course, our measure of sensibility here is exactly things like how well do the samples look, right? And how good are the likelihoods? So do we get high likelihoods on training data? And I guess when we train these models, this is our measure of sensibility, is can we learn parameters for the neural network that matches it to this predefined target? So I think for your question on sensibility, we have some quantitative ways to define that, to determine whether something's good or not. But of course, we don't really have a way to say that, well, if we think of this continuous time transformation, does it go wrong at some point so that we still get good samples but bad likelihoods? Yeah, I don't think we have a good way to think about that.
Okay, any last questions? But I think it's going to be a quick one so we can get some coffee.
Okay. Give me time. So there's just a lot that just happened. I think for me, my questions to you is that you, on my side, you introduced NFs, right? Now, what I do is I try to channel it to public understanding in a sense of like what a prof has said there by saying that he was trying to understand how did that image come about, right? So that is another beautiful way of asking it. But for me, I'm gonna ask it in the most general way again, that can this NFs beat a fair system? They cannot predict randomness, no?
Could you just repeat that last?
Can the NFs predict randomness?
What do you mean by predict randomness?
So what happens is that you give it, what I've seen is that it can give you it can predict an exact, like it can give you an exact probability of how something's gonna be, if I'm not mistaken.
Okay.
So like if for instance, if I'm watching soccer, they are faster in a sense of like if prof is playing soccer and we have samples of him playing soccer, we can have a projected way of how is he gonna score the next goal. Right? But now in Premier League, they won't have something like that because they don't use theirs is like after 25 minutes, after 40, after a certain time range. Let's say in 60 minutes, they'll give it after 25 minutes based on the data that they try to.
Okay, so where would the randomness come into this?
Oh, the randomness was the first question actually.
Okay, okay.
We'll finish
Yeah.
with that.
I think I'll give you both a chance to discuss.
Yeah, that's a good plan.
Then there's a good long tea time. Yeah, let's give another approach. I think we'll gather 22:11.
Yeah.
22:11. Thank you, guys.
Oh, good job, Emma.
Welcome back, everyone. So our next speaker is Professor Hugo from Division of Applied Mathematics, Stellenbosch University. Please welcome Professor Hugo.
Thank you. Thank you. Good morning, everyone. I'm with the Division of Applied Mathematics. There's some colleagues here. Thank you for coming. I'm also the director of the machine learning and artificial intelligence masters that we teach at Stellenbosch. So if you're interested, we can discuss over lunchtime. So the goal today is to discuss how we use nowadays many tools from machine learning in the modeling of stochastic processes and the simulation of stochastic processes. A lot of what I say actually can be applied to differential equations too. So deterministic dynamical systems. So I'll be talking about modeling using neural networks, a bit like Shane discussed before, but more specifically for stochastic processes. I don't have that much time, but I thought if anything, I should explain what is learning, what is machine learning. So I'll start with what learning is. So learning is a kind of fancy word for fitting in terms of modeling. So the usual position that we have as scientists is that we're observing the real world. So through observation, and then we gather some data, and then the goal is to build a model of that data for prediction. And so this is a representation problem. So in the simplest case, what we have is a kind of black box where we have an input, and then if we supply an input, we're going to have some output, and then we want to understand what's the relationship between the output from the input. So we want to learn, we want to infer a certain function, so that function f of x, that will give us the y. And so the goal of learning is to kind of commit to a certain model that will have parameters. I denote the parameters with theta, and then we want to find the best model for the parameters. So we want to find the best values of the parameters that will explain the data that we have in terms of that relationship. That's kind of the classical view of learning. In the modern view that we teach now to the students in machine learning, it's more of a stochastic view. So everything is a random variable. So you have to imagine that the data now is not produced by a function, but it's sampled from some distribution. So Shane was talking, for instance, about images. So when you have a sample of images, you have to imagine that that data was sampled from a certain distribution, and the goal is to learn that distribution. So it's slightly more general. In this case, now the model will be some parameterized distribution, and the goal is to fit the parameters. So to fit the parameters of that distribution using a loss. So I'll be talking about loss for doing this. And so this is the problem of learning. In the most general sense, really, machine learning is about learning probability distributions. And deterministic is a particular case of this, where the distribution of kind of singular. So machine learning in that context is the use of machine learning to carry out that task. And in machine learning, we have different areas and different methods. Machine learning is quite big. It's like me trying to explain what physics is about. So you have nuclear physics, atomic physics, astrophysics. So it's quite large, and machine learning has that kind of large span too. But this is a diagram to show the main three different techniques that are used in machine learning: unsupervised learning, supervised learning, and reinforcement learning. And the one point I want to make is that, again, it's a vast field, and it's a vast field that touches on many different subjects like statistics, mathematics, computer science, but also psychology. And there's lots of contributions coming from many different people and impacting many different people. A lot of the success of machine learning has come from the use of a specific architecture, which is very expressive, which we're using at the moment, which are neural network. There are different types of neural network. Basically, what we're using nowadays are what we call feed-forward neural networks. So it's a bit of the picture at the bottom. We have kind of an input layer, that's your X, and we have a series of nonlinear transformation that will be stacked, that will give you a certain output, and that's your Y. And the parameters will be all the parameters linking all the different nodes over the different layers. So we have what we call the weights and biases. And the picture to get is that this is really your F of theta. But this could be also the distribution P of theta. So you can generate distributions using neural network as well as just deterministic functions. So a classical problem will be classifying images as input into a label that will be a dog or a cat. And then you can train the neural network over the data to learn that classification, so to learn that transfer function. You can also make the neural network learn a distribution, so it can give you a probability over different labels, different classes. So again, there are different neural networks. these neural networks actually have been around for quite some time. People in the 70s were working already on neural networks, and even before that. And so the question is, why are we witnessing now this big expansion of machine learning and the use of neural network? And it's for different reasons. One is the availability of data. We have lots of data. We're generating lots of data now on computers, and so we have that data available. Moreover, computers now are much more powerful than they were before, and that expansion went very quick. So now we have access to huge computational power. What I see, actually, this is funny. I see students doing some things when they program, and these are things I would never imagine doing when I was a student myself, because we had limited memory and limited speed. And now there's just no constraint, basically, when students use the computer. And a third reason is that now we have many packages available for doing computations that are deemed difficult, but they're made very easy now with these packages. And this is what I want to discuss now. So we have many packages that actually came quite recently. I would say in the last 10, at most 15 years, actually, and that just make our work easier and modeling complex models, including neural networks, and handling data and large amount of data in a very, I would say, straightforward way, but easier way than coding this from scratch. In many cases, actually, coding from scratch will be impossible, and then will be prone to error, and so there will be no advancement. And so what these packages are bringing, it's a kind of uniform framework for doing computations that are quite difficult. And so it's just giving you a step into something that is quite amazing. So there are different packages doing different things. I'm just listing a few here. Keras was one of the first one integrating neural network in a uniform framework that was later integrated into TensorFlow. TensorFlow comes from Google. So they hired actually people behind Keras. It focused on neural networks initially, but then it went on to expand into probabilistic models. So there's lots of tools about probability theory, random variables, and distributions. PyTorch comes from Facebook, Meta. So the goal there is the same. It's kind of competing package. And then lately we've seen JAX. JAX is also from Google. This is a tool actually aimed at speeding a lot of the computations that we do on big data, and then computation that having to do with neural networks. So it's not so much about representing neural network. You would do this in TensorFlow, but you can accelerate all of your computation using JAX. And then on the back of this in Python, there are many, many sub-packages that will be related to probabilistic models like random forests or classifiers or support vector machines. And these are parts of different packages. One that I'm listing here, which is very important, which students use a lot in machine learning, is the scikit-learn package, which is more towards statistical analysis, not so much neural network. So with this, we have these packages available. As I said, you can handle complex models more easily. And also these packages have been optimized for GPUs and TPUs and are available also online in the cloud. So a lot of times you're not even running anything locally on your machine. And so you have access to huge computational power if you want, and have a certain budget actually also to spend on computational power, but it makes computation cheaper and easier. And so this is the really big step for us. So this has been applied in many different areas in science. So if you think about machine learning in science, there's basically two ways you can approach this. You can use machine learning tools as a way to do your own science. You can be in physics and chemistry and simulation. And the other side of the coin would be to actually use science to understand machine learning. Okay, so I'll talk about the first one. So there's lots of machine learning tools that have been applied now in particle detection. For instance, if you look at the CERN detectors, there's really no one looking at the data now by hand like they used to up to the 80s, 90s. More recently, they really have machine learning tools that will do the classification of particles automatically. And so you can guide, and it's easier because you have lots of data. Fluid simulations, the same. Material design, now you can screen through thousands of possible material before to see which one has any potential to solve what you need in terms of functions. And you can do this using machine learning to single out the possible candidates that you can synthesize and then have more chance of finding something useful. Protein folding was also something that was tackled recently using machine learning, specifically reinforcement learning, and that was the subject of last year's Nobel Prize in chemistry. And now we've seen a new application coming from DeepMind again, which is weather prediction using neural networks to do better weather prediction. The other side I mentioned is that a lot of physics now is being used to understand why machine learning works and why neural network actually work. This is something that's still not so clear for us, actually, that by stacking all these neurons and connecting them and having nonlinear function, you can represent any kind of function, however complex they are. And so there's still a lot of work in trying to understand that. So what I want to talk about on my side is how we use these tools for doing modeling of stochastic processes, simulations of stochastic processes, and the analysis of stochastic processes. And at the moment, I have 3 projects that I'm listing here. So the modeling, the rare event simulation, and response. And then with the time I have, I'm going to discuss the third one, response. But first, I want to discuss the other one. So the modeling is the usual modeling question. You have data, you want to fit a model to that data in order to do predictions. So for us, the model will be a certain stochastic process. So that's that state that depends on time, x of t. It will be like a differential equation, but you have noise built into the system. The parameters might be uncertain, random variables. So that makes the whole system a stochastic system. So this is a physical system. It could be diffusion models. It could be a man-made system like stock market. So you have stock prices changing in time. And so again, the goal is to fit a certain model. What we used to do is to come up with low dimensional model because we were limited in the way that we could actually represent this on computers, but also do the learning. But now with neural network, it's easier to actually come up with very complex models that we might not necessarily understand, but the prediction will be better because there'll be a better fit with the amount of parameter, with the large amount of parameters that we can consider. So what we do is, Shane actually mentioned this a bit, is that we can represent the different elements of the dynamical models using neural network. And with the data, we can minimize a loss or do the training in order to find the best set of parameters that will fit the data. And then once we have this, then we have a generative model. So namely, we can do prediction, we can simulate the model in order to get new trajectories. We can simulate many trajectories if you have a stochastic process to do probabilistic prediction. Calculate, for instance, what is the probability that the system will reach some region in time at some later time. And so this, you would do this for weather prediction, but you can do this for many different systems as well. So that's for the modeling. And again, the packages will make that simpler, and I'll show actually some code later on in how we code things and how the packages are structured and what kind of syntax we're using for this. My own research over the year has focused on what we call rare event simulation. So you take a stochastic process and you want to calculate certain events or probabilities of events happening, but the probability is very low. For instance, if you have a stock, what's the probability that the stock goes bankrupt, so to the zero price, or if you have defaults in a financial system. So this will be a very small probability. We're talking 10 to the minus 6, 10 to the minus 10. And if you do a direct simulation, you will never see those events because they're just very unlikely. So direct simulation doesn't work. So you have to actually change the way that you simulate the system to enhance the realizations of those events. And then we do this using what we call importance sampling, which is a technique that's quite old actually in statistics, which is you guide your process, you change the dynamics of the process to actually move it in the region of interest, and then you can just you can unbias that guiding in order to get the original probability. Okay, so this is something quite nice. But the way that you guide this process can be very complicated depending on the complexity of the system. It involves a lot of control techniques that are based on gradients. And again, that calculation in the past was quite complicated. And so we would limit ourselves to very simple models in order to do this. But now it's completely open with the package to include many particles, include many dimensions, and so on, and then just run the thing without really thinking much about the implementation. So these are the challenges for the modeling, but also for the rare event simulation, but they are also challenges for the response. So response is a specific question in the modeling, which has to do with once you have a model and then you can do simulation, often you want to predict what will be the change in behavior by just changing some parameters. And this is very important in finance. For instance, it's related to risk, because you can imagine that if you're fitting a model, but actually you're making some errors in inferring your parameters, what is the effect of the error on the inference on the prediction itself? And so you have to see what's the sensitivity of your model, what's the response of your model, and that relates to taking a derivative. You have a lot of parameters in the model, and you want to see what's the change of behavior as you change these parameters, and so what's the derivative of the model with respect to parameters. So that's the last one I will discuss. So this is what we call stochastic response. I'm just going to phrase stochastic response in a very general way as something related to random variables. And then later on the next slide, I'll show you how we can apply the same ideas now, but for a stochastic process. So imagine that you have a random variable. It comes from a certain distribution, and that distribution involves some parameters. So X is distributed according to some P of theta. Often what you'll do is that you're going to have some data that comes from that distribution. You're not observing the data itself. You're observing what we call an observable. It's some function of the random variable. And often also you'll do a kind of averaging. So what you consider is an expectation. So that's the E sign there, an expectation of some function of the data of the random variable. So the function can involve parameters on its own. So I have these parameters as nu, and the parameters for the random variables will be theta. So the observable depends on the theta and the nu, and then you want to calculate the response with respect to those parameters. So you have the choice of taking a partial derivative with respect to the parameters of your model, or a partial derivative with respect to the parameters of your observable, so the function that you look at. So the way you would do this empirically is that you have a whole bunch of data, and then you have an estimator for the observable. This is what you observe, and then you have a running mean over your observation, and then you want to take a derivative with respect to the parameters. Now, in the old way, what we would do is that we would do two simulations, a simulation for theta and a simulation for a slightly different theta, and then we would take a finite difference to calculate the derivative. But nowadays, we don't have to do this. Nowadays, you can code your estimator, and then you can ask the computer to calculate a gradient directly onto the program. And how this will be done actually will just follow the chain rule, because any function is just a composition of functions. So you can push a gradient onto your program, and this is what we call automatic differentiation. So all the packages that I've mentioned before, TensorFlow, PyTorch, has the capability of differentiating any function that you write as a program. It can even differentiate any program itself. So any kind of simulation that you have that will have parameters, you can apply a partial derivative operator onto that program. And the program, PyTorch or TensorFlow, will go through your program to calculate what the derivative would be. And this is an exact derivative. It's not a finite difference. It's not a symbolic derivative. It's a third kind of derivative that we call an automatic derivative. So this is what we use to do simulation. And here's an example. So I'm going to take a Gaussian variable. I take the exponential of that Gaussian variable. I know from statistics that this will be a log normal. And I want to calculate the response with respect to the two parameters of the Gaussian, namely the mean and then the variance. So I have this expectation, that's the observable, and I want to calculate the derivative. Now, I can calculate the derivative actually exactly, and so I'm showing what the answer would be. But if I didn't know the answer, what I would do is that I would just get many, many samples of X. I would take their exponential. I would take the sample mean of the exponentials, and then I would try to calculate the derivative. And so we can do this directly, and then here I'm showing what the code would be in PyTorch. So this is Python code. I import torch, so that's importing the PyTorch package. And then from the PyTorch package, I can import the grad operator. And so the grad operator is the derivative operator. Now, in my code, I have the definition of my estimator. And so this is what you would write as your estimator. And then the goal is to get the derivative of that estimator. And it's as simple as taking grad of the estimator function. So when I write the grad there, nothing is evaluated. What the program would do essentially is to go through your program and apply the chain rule bit by bit to calculate what the derivative of that program would be, or what the derivative of that function would be with respect to the parameters. So with the argnum 0, it means I'm taking the derivative with respect to the first parameter. So this will be the grad with respect to mu, and this will be the grad with respect to sigma, because it's the second one. And now here, I'm actually calling the grad for specific values of the parameters. And then the one thing you need to do in PyTorch is just making sure that everything is a tensor in PyTorch. Okay. In fact, in machine learning in general, now everything is a tensor. So even scalars are tensors. So you define those as torch tensors, you set values, and then you can calculate the values. And so here I'm doing this for, sorry, it's a bit small there, but I'm doing this with different values of n, and then the computation will just be direct. Again, it's the exact derivative. So this is the exact response for a given sample that I don't need to recalculate. And then I see the convergence. The convergence is a Monte Carlo convergence. So you would see the 1 over square root of sample size convergence. But the point, again, is that I'm not calculating a finite difference. I'm not calculating a symbolic derivative. I'm calculating a numerical derivative, but which is exact. And so that's the automatic gradient. So doing this when I was a student would have been impossible, but we would have laughed. If you had said to me that you could do this computationally, we would have been, you're not serious. You cannot do this. But now it's available in packages as just one function grad, and then it's just transparent. The first time you're going to call the function is going to take a little time for the computer to actually generate what we call the computational graph, which is the whole sequence of what the grad should be. But once this is generated, when you call the grad, it's not recomputed. So then it's very quick. And in fact, the complexity of taking the gradient is exactly the complexity of your function. There's no added complexity except generating that graph initially. And so this is very efficient, at least as efficient as your simulation. So what I want to indicate now is that we use this at large, but in stochastic simulation. So here I'm putting the example of stochastic differential equation. So I have a differential equation plus noise, so it becomes a stochastic differential equation. The drift part of the equation has some parameters. The noise part of the equation has another bunch of parameters. And so I have the dual task of first learning the parameters from the data. So we do this. This is the modeling question. And then we can use the SDE, the stochastic differential equation, to generate more trajectories and so to start doing prediction. But we can also compute response. So in this case, the stochastic differential equation will be simulated. I can observe different things about this dynamics. This will involve some parameters, and then I can take the automatic gradient of that observable to see what will be the response of these observations with respect to those parameters. And now what you have to imagine is that when I take the gradient will go inside the full dynamical simulation to grad everything. And this is massive. And again, the computational tree will be simulated once, generated once, but once it's generated, the grad will just rely on that map in order to calculate what the gradient of everything is. So you can imagine simulating, I don't know, 10,000, a million particles over a very long time, and then you're grading all that simulation at once in order to get the response. So in one simulation, you get your prediction, but you get also the response in the same simulation. Okay, so this is what we do for different things. So for instance, we do this for the modeling. So in terms of financial modeling and risk analysis, and then the response for looking at a financial response. So for instance, the observation in this case could be some options and things like this, and they want to find what will be the response with respect to parameters in your own model. But we do this, especially now with students, for the rare event question that I mentioned before, calculating the very small probability of events that are difficult to reach. And then we use machine learning. We use the grad actually to guide the system. So we need to be able to calculate the grad of stochastic simulation. Okay, so this will be a kind of simulation that you have. So it's here, I'm just putting the skeleton of what a code would be. So again, you're importing Torch and then the grad. And then there's a sub package in PyTorch actually, which is Torch SDE. And it's a very nice package. It's been designed to do the simulation of stochastic differential equations at large using different types of integrators, but also different conventions for stochastic differential equations. So it's something that we use a lot, and it's been designed in a way that you can grad anything in that package. So everything is actually connected. So what you need to do is that you need to represent a certain model. So you would define first the drift. So that will be the F there. It involves some theta parameters. You would need to define what the sigma is in your model. You have another bunch of parameters. Then with these two, you can define the SDE itself in a way that's consistent with the syntax of Torch SDE. In order to do the modeling, the fitting, you would define a certain loss, which will come from the trajectories, so from the model itself, from the SDE models, and then from the data. And then at that point, you would have some kind of training that would evolve on its own a grad in order to fit the parameters. So the fit loss will be the modeling part. You fit the parameters. Once you're done with that, you can use your model to generate new trajectories, to do prediction. If you're looking at specific observable, you would define also that observable. It involves some parameters. And then at that point, you can look at gradients. So calculating gradients and response is no more difficult than actually setting a model and learning a model. And this is the amazing part of this. So here I'm showing an example that has to do with a two-dimensional system. If you have access only to X and Y coordinates, you can learn the whole vector field of a differential equation. But what's new now is that you can learn also the noise part of a stochastic differential equation. So the modeling also works for stochastic processes. And this works also for jump processes, so population models, Markov chain. It's not specific for stochastic differential equations. Okay, so I just wanted to give you an idea of what we do with this and what's available. I would really encourage you to have a look at this. If you're doing any kind of dynamical simulation, there's lots of tools that can help you coming from machine learning that weren't necessarily designed actually with the applications you have in mind, but these are very useful tools that might be useful for your own research and your own purpose. So really have a look. You can ask ChatGPT, actually, if you have applications. It's a good tool to learn new packages because there are too many packages in Python. Nobody knows all the packages available except ChatGPT. So if you're interested, I'm giving also some references for on machine learning. One that's quite nice that appeared just before COVID, and then I think it was like that everybody in physics read at the time during COVID. It's the first one. I really recommend this one. This is a big tour of machine learning at large, supervised learning, unsupervised learning, and reinforcement learning. The second one is more specifically how machine learning tools are being applied now in the physical sciences. The third one is about neural networks and what's the architecture of neural networks and how you can code them. The same for the fourth one. And the last one is kind of the little Bible on deep learning, but not so much on the coding side, more on the theory side. It's quite a big, thick book, but it's for free on the internet, so you can have a look there. So I'll finish here. Thank you.
Thank you very much for Professor Hugo for such a nice talk. So let's first talk if we have any question from the online audience first. No. Okay. So yes.
A practical question on the application of auto differentiation to physics simulations. Often you have a situation where these simulations are extremely long,
Yes.
Especially if you're looking at asymptotic behavior. So in that situation, the auto differentiation, when you're trying to optimize some parameters, then it actually takes quite long to do a single step. So my question is, do you deal with situations where you have these long simulations, and is there a practical way to overcome this limitation?
Not really. The complexity has to be the same complexity as your own simulation. So the grad complexity is really the same because it's the chain rule applied to your simulation. And if you imagine like naively, you would take a finite difference, which would be two function call, like two simulations. So at least you can do better than doing two simulations, but I don't think you can accelerate the grad with respect to your own simulation. So I think you just have to be you'd have to think about how you can speed up your own simulation, or maybe taking a grad that's not taking the full time span of the simulation, or maybe not the full system. So we do this a lot. For instance, you calculate the response for a much smaller system, hoping that it's representative of the bigger system. So this works a lot in physics, for instance, because when you're simulating systems with a lot of particle, considering 1,000 particle might be just as good as simulating 2,000 or 3,000. You have this idea of the thermodynamic limit in the background. So, yeah.
Okay, thanks. Yes, that's clear. Thank you.
So, based on the graph that you figure out the response, can you use that to reconstruct a proxy of the symbolic equations, giving rise to the
the derivative.
Yeah.
We don't actually see that computational graph. This is calculated in the background by PyTorch or TensorFlow. This is just a recipe for the computer to calculate the grad. It's saved somewhere in some form, but we don't see it explicitly. I'm not even sure you can read it. But the point is that when you call grad just then relies on that computational graph to calculate the grad. And so essentially the computer writes another program, another function to calculate the grad. And whenever you call grad now, it just calls that function. But this is done automatically. This is what's great. And the reason why it can be done automatically is, this, a derivative can always be calculated. An integral cannot always be calculated. So you could not do automatic integration, but you can do automatic differentiation.
Thanks. So correct me if I'm wrong, but my understanding is there are different ways to do autodiff, right? So backpropagations and neural networks, that's autodiff, but you also get these hyperdual numbers, which are kind of popular in Julia. And then even with hyperduals, you get a forward mode and a reverse mode differentiation. So are there clear winners in terms of which of these algorithms form the best and the fastest for auto differentiation? So, and just to give you an example, I've got a PhD student who's working in thermodynamics, and they take lots of partial differential equations, but they have to take the partial differential equations of functions that are calculated iteratively, so root finding methods, etc. And we're actually like it's not that straightforward to use the hyperdual numbers with autodiff. It's quite challenging. Yeah. So what's your opinion on the different methods?
So I'm not so aware of how Julia does it with these dual numbers. I would be interested to actually have a look. So there are different ways of taking the automatic gradient, and it depends a lot on what's the dimensionality of the input versus the dimensionality of the output. So for instance, the reason why backpropagation is used for neural network is that in most applications, the input is high dimensional and the output is low dimensional. In this case, it's more efficient to take the derivative in a backprop way. If you had the other situation with a low dimensional input and high dimensional output, then you would do forward differentiation, not backprop. So I think there are ideas like this. Then in terms of implementation, I'm not so sure, actually. I don't know enough to say whether one method is better than another. And it would depend a lot on implementation also. So I've been comparing, for instance, TensorFlow with PyTorch, and there are differences. There are differences in syntax, and there are differences also in performance, and also in JAX. So I think it would be interesting to compare. And there hasn't been a lot of comparison, mostly because these companies don't want to communicate with one another. They don't want to benchmark between themselves. And these packages are quite recent too. So there hasn't been a lot of comparison at the moment. JAX is not even at version 1.0, but it's been at version 0 point something for more than 6 years now. Yeah, so there's still lots of work. There's lots of development. I'm telling the students right now in machine learning that this is an amazing period to be in terms of tools being available and then doing coding. But in fact, I'm saying this, but in 10 years' time, it will be completely different too. In 20 years' time, will be completely. So the tools are always evolving and becoming more powerful, and something, it just brings possibilities. Yeah, but I'll be interested to compare and then understand these more.
We have one question from the online audience. I was wondering if you have experience with the Kalman filters or extended Kalman filters for time series of forecasting. Do you think these methods still hold potentials, or are there limitations that could be better addressed using generative AI approaches?
So I'm not an expert in Kalman filters, but I would say that whatever you can do classically in terms of modeling and in terms of applying different models for time series prediction, everything can be done now in a framework where automatic differentiation is available and might be useful for applications. So, if you want to develop Kalman filters, you can do this in PyTorch, you can do this in TensorFlow, just like you would in any normal environment and languages. The benefit is that you just have a lot more packages available for yourself in terms of representing what you need to represent and then handling what you need to represent also.
Any other question?
Prof, actually, I want to seek the guidance actually. While solving, when we solve the differential equations using neural networks, there are some research articles on that in which only a single hidden layer is used. And in some solving differential equations, there are multiple layers are used. Hidden layers are used to construct the neural networks.
Solving differential
Yeah, while
equations,
solving
stochastic
differential
yeah.
equations. Okay. Which the learning affects whether we increase the number of hidden layers or if we get the output by only considering a single layers. So what makes the difference between it and how the neural networks train like that? If we consider the more number of layers, it will train better, or if we can get the output by only considering a single layers,
Yeah.
then it will be which is the appropriate way and how's the learnings actually.
Okay.
I need your guidance about it.
Yeah. So first, I should say that I'm not using neural network to do the integration of the stochastic differential equation or the differential equation. So I'm using just normal integrators for solving the stochastic differential equation. So you can use neural network also to solve differential equation and to solve stochastic differential equation, even partial differential equation or stochastic partial differential equation. That's another topic. For us, we use neural network to represent the model itself. And then once we have the model, we just do the integration like you would normally do using Euler scheme or Runge-Kutta scheme or whatever. But the model itself has some representation. In the representation of the model, there's a neural network that's used there. So that's the first thing. Then the choice of the neural network depends on a lot of the kind of application you consider. So if you consider a low dimensional system or just few particles, there's no need to consider a very deep network with many layers and many nodes. And so, but that choice is informed by some experience in how expressive neural networks are and what kind of application or use you want to consider. You see, so in machine learning, I mean, except for the big companies and ChatGPT, we don't consider huge networks or many layers. I mean, deep learning, the joke is that if you have 2 layers, that's essentially deep learning. If you have more than 1 or more than 2, that's deep learning. So even for myself, for the models we use, we never go beyond 3 layers. And then the number of nodes, you can enlarge on the number of nodes, but the number of layers, you don't have to go very deep. It's a different game if you consider really large scale simulation of millions of particles over, if you do kind of weather type prediction, then you would need deep neural networks and large neural networks. But you need to trade off, of course, on the possibility of simulating those on your own computer or the computational resources that you have.
I have one more question. Was there any other question? Oh, okay. Because we are running, yeah, we'll catch up later. Oh, you can ask, but anyway, so I just wanted to ask you, go from the, thank you for the presentation. Just, you spoke a bit about computational power and the fact that, we can access these packages on the cloud and so forth. But are you able to tell from your side, is there any risk that we should be aware of? So for example, we have now received something which tells us, okay, we've got countries of concern. And in some research groups, when we apply for funding, they want us to indicate which countries we are working with. So from these resources that we have, I mean, they are on the cloud, there are people collaborating.
Yeah.
Do you see that continuing? Do you see any, I mean, as a university, should we be thinking about our own platforms? I know it's very expensive, because
yes,
usually we can't afford a lot of things. What sort of advice would you give?
It's just my personal opinion, but I don't think there's a risk at the moment because most of the computational power is in Europe and the US. So as that's to consider. There's not a lot of cloud computing that's available in China. It must be a lot for themselves now. I'm sure that they have lots of cloud computing power over in China, but that's not open to us. So again, it mostly is in the States and Europe. There's lots of cloud computing in Europe too. So I think on that front, I think we're good for the time being. The question of whether we should invest ourselves in computational power, I think, is a very good question. It's very, very expensive, and my advice is to consult with the community to see what kind of use actually we have at the moment and what we need in the not so far future. We had that discussion, I remember, just before COVID, and then the decision was made not to buy an HPC or to upgrade the HPC that we have. The HPC that we have is old and not really great, but there's an HPC in Cape Town. If you look at different countries, actually what countries are doing now is to invest in computing resources at the level of their own country and not individually in terms of institution, because the cost is too great to an institution. So I would suggest getting an HPC for South Africa and then looking at the use there and not for Stellenbosch specifically.
Let's thank Professor Hugo for such a
Thank you.
wonderful talk. Our next speaker is Professor Nick Hale from Stellenbosch University.
Yes, Nick.
Professor, over to you.
Thank you.
Not right.
I got this one. Okay, good morning, everyone. Thank you to the organizers for the opportunity to speak today. We've heard a lot of interesting talks so far about the analysis of differential equations and modeling with differential equations. It's my job today to talk about the hammer that was mentioned yesterday, which is numerical methods for solving these. Right? Eventually, you're going to have to get your hands dirty. You're going to have to solve a differential equation or get one of your graduate students to solve your differential equation for you. But what I want to get across today is that not all hammers are the same, and there may be some other different options of numerical methods that might be worth considering in some options. And that's these ultraspherical spectral methods that I want to talk to you about. So if I say differential equations, most of you immediately think of maybe finite difference methods, possibly finite element methods if you have a more engineering background. If you've done some harmonic analysis, maybe Fourier-based methods. But I want to talk about spectral methods, which are usually polynomial-based, but the difference is that they are global in nature. So whereas finite difference approximations do local approximations with typically polynomials, spectral methods are global, which leads to higher order and faster convergence, although in some situations it makes them a little bit more restrictive and maybe more expensive. But by looking at what I'm going to call these ultraspherical spectral methods, you can maybe get around some of those things and end up with very high accuracy methods. So we're aiming for 10 to 15 digits in our approximations, but they're also very fast. So maybe linear time solves in the number of degrees of freedom that we have in our discretizations. So why am I talking about this at this workshop in AI and dynamical systems? Well, partly because Ali asked me to, but there are connections. So Hugo was talking about forecasting. So if you want to train a model over a very long time simulations, you really want those simulations to be as accurate as possible. So you're not training your model on the noise. And particularly if you're looking at training physics-informed neural networks or neural operators, which are a combination of sort of data-driven modeling and classical differential equation modeling, you really want to be able to do that quickly, especially when these systems are very large. So that's why we need these fast solvers too. Okay. So hopefully what I'm going to talk about is, or show you, or convince you, is that sometimes a hammer can also be a key. And so what's the quick outline of this talk? Well, I first want to tell you what a classical spectral method is before talking about these ultraspherical spectral methods. And in particular, I want to talk about some extensions of these ultraspherical spectral methods that touch on some of the other topics that have been mentioned in the last couple of days. So we heard talk about integral differential equations with convolution kernels. I mentioned those. And we also had a talk about fractional differential equations. I'm not sure how we can get these spectral methods to perform that. So I probably have too many details in this talk. So here's the executive summary and the things that we will need to look at as we're going along for. The conditioning I'm not really going to talk about too much, but we want exponentials of very fast convergence and linear times of very fast solves. And how we're going to do that is we're going to look for banded differentiation matrices and conversion matrices. So when you see those things come up as I'm going through, that's the thing that we're really looking at. Okay, so like I said, I'm first going to introduce standard spectral methods for you, and this goes back to, I think, the 70s with Orzag at Princeton. But the idea is based on maybe something that you would have seen at undergraduate level, which is polynomial approximations to
the solution of your differential equations. So here's going to be my toy differential equation that we'll start with first, and I'm going to look at boundary value problems in particular. So the idea is that you assume that your solution, and I guess the right-hand side in this case, have a convergent power series expansion. That's a pretty bold assumption for a boundary value problem. We'll come back to it. And then you just plug it in, right? So if this was the power series expansion of our solution, well, we could differentiate it twice, so we'd end up with this. And that will lead to a recurrence relation for the coefficients in that the coefficients in the solution, right? And we could also think about the boundary conditions, right? If we plug that into our expansion of the solution, we get, again, a condition on the coefficients that needs to be satisfied, right? And this is a linear equation, so nicely, we could write that in matrix form. And it would look like this. This is exactly the linear system you would get if you tried to find this solution. And I'm going to refer to this as an almost bounded linear system. So what do I mean by that? Well, it's almost bounded. So a bounded matrix would be a matrix which only has a finite number of non-zero diagonal entries. So that's this part here. And it's almost that because, well, I have a finite number in this case, or an n-independent number here, 2 dense rows at the top. So that's what I mean by almost bounded. And it turns out, I'm not really going to go into the details, there are lots of nice methods in numerical linear algebra for solving linear systems of this form. And this approach works sometimes with these power series expansions if our assumption of the power series being convergent is valid. So here is what such a discretization would look like in MATLAB. Here's what the solution looks like for this problem. And here's the convergence. It worked very well. Okay, so why do we need to talk about something else? Why isn't this good enough? Well, like I said, this assumption of a convergent power series is usually not going to be true. And also there's ill conditioning. So this problem was chosen very carefully so that it would work. If you perturb the right-hand side here by a little bit with some rounding error, this convergence goes away. You don't get this fast convergence. So the standard idea, Orzag's idea was, well, instead of using a power series as our expansion of the solution, let's use what's called a Chebyshev expansion. So essentially, it's still a polynomial basis, but we're using these Chebyshev polynomials rather than powers of x. Just a bit of notation. I mentioned at the beginning, I was going to talk about differentiation matrices. And so we sort of seen those for these power series. These are the matrices that if I had my power series expansion of my solution, and I think about a vector of those coefficients, if I multiply that vector of coefficients by these matrices, that gives me the vector of coefficients in the derivative, or the second derivative for the second derivative matrix. That's what I mean by a differentiation matrix. So that linear system we just saw on the previous slide, we could write in this form. Okay, so why do we want to think about Chebyshev polynomials? Well, they have much nicer convergence properties. I'm not going to go into the theorems, but the key one is this one. If your solution is analytic in any neighborhood of your interval that you're solving your differential equation on your boundary value problem, then these coefficients would decay geometrically, so exponentially fast, which is not the case of power series expansions. You need a circle of analyticity in the complex plane. So these have much nicer convergence properties. Let's take that away. And there's also connections with fast Fourier transforms, which I've mentioned previously, which enable these things to be computed very quickly. Okay, so how does our example that we looked at previously work if we were to use Chebyshev polynomials? I haven't given you the details, but they give rise to these differentiation matrices, which are a little bit more complicated than our power series, right? And in particular, notice they're not bounded anymore. So those it will be an upper triangular matrix in both cases. I'll come back to that. But you could again apply the same idea. You take your Chebyshev expansion, you substitute it into your differential equation, equate the coefficients, and you'd end up with, again, a linear system that would look like this. Okay? So we've solved the problem of the power series not being convergent, but we still have some other problems. In particular, we now have a dense matrix, right? We lost that almost bounded structure. We end up with something that instead looks more like this. Okay, so that's classic Chebyshev polynomials. What are these ultraspherical things, and what's the aim there, right? So to recap what we did, we spoke about power series, but they don't converge very well most of the time. But they do end up with a nice linear system in terms of its structure that we would like to keep. Chebyshev converged very well, but ended up with dense matrices. We want something which has all the green things, all the good stuff, but gets rid of the bad stuff, right? So we'd like nice convergence, nice conditioning, and this fast linear algebra that enables us to solve things very quickly. So how do we do that? So my collaborators, Sheehan and Alex, who I do from my PhD, they come up with this. And here's the idea. The idea is that you stick with Chebyshev, but you mix your Chebyshev. So I spoke already about the Chebyshev T polynomials, which is one basis of polynomials. There's another kind of Chebyshev polynomials called Chebyshev polynomials of the second kind, which are very similar. You can write them down like this. It doesn't look like a polynomial in this form, but trust me, it is. My third years never believe me either, but it's true. And the key observation is this. If you have a degree n Chebyshev polynomial and you differentiate it, and you write the result in terms of the second kind Chebyshev polynomials, it again turns out to have a short-term recurrence. Right? So rather than involve all the Chebyshev polynomials of lower degree, if I write it down in T, if you change basis at the same time as you do your differentiation, you get, again, a banded differentiation matrix. Right. So then let's apply the idea, right? Let's, again, expand our solution as Chebyshev T, substitute it into our, and now I'm just going to consider a first-order differential equation, and apply that, that rule here. I'd have this. And now our second step that we did with our power series was to equate coefficients. But now I have a problem because, well, I can't equate coefficients when I have different terms in my equation here in different bases. I need to convert everything to the same basis, right? So I could convert U back into T, and then everything would be in terms of T, and I could compare coefficients. But that's what we just did with standard Chebyshev, and it didn't work very well because, well, I wouldn't have my banded differentiation matrix anymore. So instead of turning the U's back into T's, we're going to turn the T's into U's, what's called using this, again, short-term conversion operator. Right? It turns out, again, there's this nice connection between these two orthogonal polynomial bases, and I could write everything in terms of U. Look like this. Again, now everything is in the same basis. We could compare coefficients. We ended up with our linear system of equations to solve. And in this case, again, it's going to be banded because both of these operations here were banded. Right? Why does it become almost banded? Well, we still need to apply some boundary conditions, but we could do that and it would look something like this in this case, right? So it's well conditioned. Again, I'm not really talking about that, but you'll believe me, it's almost banded, so we can solve in linear time. And because we're using this Chebyshev basis, as the theorem said that I sort of glossed over, we can expect exponential or geometric convergence. And you can do the same thing for higher order derivatives. That's where these ultraspherical polynomials come in. So they sort of generalize this idea of first kind Chebyshev and second kind Chebyshev. You sort of go up this family of different orthogonal polynomials, what we call the ultraspherical polynomials. And again, the details here aren't important. The key thing is that, again, we have these similar relationships between these ultraspherical polynomials as we did between the two kinds of Chebyshev. So you end up with a banded differentiation matrix because of this short-term recurrence for the derivative, and you end up with a banded conversion matrix because of this short-term recurrence for the conversion operator. Okay, and so you can combine all those things and you can do higher order equations. I'll just quickly show an example. So here's the first example we had with that we did with the power series. But here, if we were now doing it with these ultraspherical method, we again end up with a almost banded linear system, and we get this exponential convergence. And then they also showed how to extend this to higher order. So we could do fourth order, eighth order. I think they even had a 10th order equation in their paper, non-constant coefficients, and also PDEs by taking tensor products. Okay, so that's just ODEs. But as I said, we like to extend this into doing more complicated kinds of differential equations. And so one thing Alex and I looked at was, as I said, convolution type integral differential equations. So here's an example. So we have derivatives, so it's a differential equation, but also an integral there. And this is a convolution kernel, right? Because we have t minus s, where t is the independent variable of our solution, and s is the integration variable. So how does this work? Well, the idea is very similar. In order to do the derivative part, we're basically going to do the same thing as we did for the ultraspherical polynomial. There's a slight caveat. Instead of using Chebyshev polynomials, we're going to use Legendre series, Legendre polynomials, which again is very similar. They're orthogonal polynomials. You have lots of the same nice properties. I'll show you on the next slide. And the reason we do that is because Alex and I had a previous paper on how to convolve these Legendre polynomials. And if you're doing something with a convolution kernel, you need to convolve those two polynomial series, then we could use this relationship that we'd already worked out. Recently, someone showed how to do it with Chebyshev, but I didn't have time to update my slides, so we're going to stick with Legendre. So again, this slide looks a lot, but it's exactly the same as we had for the Chebyshev case, right? All I'm doing is saying if we expand our solution in terms of Legendre polynomials, we can end up with a banded differentiation matrix, a banded conversion matrix, and we end up with a banded linear system of equations. So that deals with the derivative part in our integral differential equations. And then for the integral part, as I said, we need this relationship that we worked out. And it turns out if you have the Legendre series coefficients for your kernel in your integral differential equation, you can construct this matrix V, which very much similar to the convolution theorem that you would have done if you'd done any Fourier analysis. You can write as a matrix times the vector of the coefficients of the solution variable. And again, it turns out very nicely that if your kernel is polynomial, or if it can be well approximated by a polynomial, you end up with a banded matrix. So that was for a Volterra type operator, right? So a Volterra operator is where you integrate up until t, which is your independent variable. You can do the same thing for Fredholm operators, where you integrate up until your final time. I think I have an example. It doesn't matter too much. So here's an example. So it's a differential equation. We have the second derivative here. So we're using those banded differentiation matrices we spoke about. We have some non-constant coefficients. I didn't really tell you how to do those, but that's not really a problem. And then here we have this convolution type kernel, right? It's non-separable, right? Separable would mean we could write it as the product of a function of f times a function of, sorry, a product of t and s, and just separate those, but we can't do that. So here we end up with discretization that we used, and here's our almost banded matrix, right? The bandwidth is bigger here now, and the bandwidth here will depend on how many terms we need in the polynomial approximation to this. That will make it bigger, but that won't increase as we increase our discretization size, right? So you can still say it remains banded. And here we're seeing, again, we're getting exponential convergence for this problem. Okay, and so I'd also briefly mention fractional differential equations, which we saw, was that Wednesday, I think? And a brief history of fractional differential equations. So think of a famous mathematician, and they at some point looked at fractional derivatives. But I think the first ones to do this were Leibniz and L'Hopital, where they sent a letter to each other. And one of them asked, well, what does it mean to take a half derivative? And the other one said, I don't know, but it will probably be useful in future, which hopefully we're getting to now. And in fact, that's true. There are lots of application areas, as we saw, finance, but also in physics and epidemiology. People are interested in these kind of things. And so how does that relate to our octaspherical spectral method? Well, first we need to define what we mean by a fractional derivative. And in fact, I'm going to look at fractional integrals before. I'll come back to derivatives in a minute. The standard definition that people use is what's called the Riemann-Liouville fractional integral, which looks like this. And you can basically think about that in terms of repeated integration. So if you were to do two integrals, you could write that in such a form. And then you generalize that by saying, well, let me rather take a fractional number of integrals rather than an integer number. And it works as you would expect. So if you do a fractional integral of a polynomial, then you sort of integrate up by, let's say, half, if you had a half derivative. So how does this relate to the octaspherical stuff? Well, what Sheen and I worked out in our paper is that if you would apply this idea for, let's say, the half order to keep things simple, if you think about the half integral of a Legendre polynomial, you can write that as a difference of two Chebyshev polynomials. And again, it's a short-term recurrence. It only involves two of these guys, right? Not a whole sequence of polynomials from degree n down to degree 0. The complicating factor is that it by definition of those fractional integrals, it integrates a singularity at the left, right? But then the other convenient thing is that if you think about taking the half integral of something that looks like one of these, right, a singular weighting times a Chebyshev polynomial, it turns out you can write that again in terms of a short-term recurrence in Legendre polynomials. So again, we end up with these short-term recurrences that give us these banded linear operators, which are nice, right? It's very easy to solve a banded linear system of equations. So these operators look like this. Now, there's no way to go between these two spaces, though, because you can't get rid of that singularity, right? If you start with the smooth thing, you get something singular. And if you start with a singular thing, you get something smooth. So the way to get around that is to take a basis, or maybe more accurately, a frame that captures both that behavior. So you have a smooth part and a singular part. But you could apply these operators to each of the different terms, and it works out nicely. So I think I have an example. It looks like this. I think there's a better example here. So if you do that, here's our banded fractional integration matrices. And here's the equation I'm solving. So it has this identity part here, and then the fractional integrals. We're applying that to the two different terms in our sum. You end up with something that looks like this. It doesn't look banded at the moment, but it turns out if you interlace these coefficients, so go A0, B0, A1, B1, and so on, you do end up with a tridiagonal system. Right, so it's almost trivial to solve very quickly, and you still get the geometric convergence because your underlying basis is still these orthogonal polynomial expansions. So it works nicely. Okay, that's what the solution looks like because you were all wondering, I'm sure. And fractional derivatives are very similar. So I'll briefly say there are different ways of defining fractional derivatives, even if we take our fractional integral to be the one we had. So basically, the Riemann-Liouville, you do a fractional integral and then you differentiate. And a Caputo fractional derivative, you differentiate first and then you do the integral. Slight differences there. We can do both. I'm just going to look at the fractional Riemann-Liouville definition. And again, just very quickly, the key thing is that what we realized is, again, if you look at the fractional derivative now of a Legendre polynomial, you can write a short-term recurrence in terms of Chebyshev polynomials. And if you look at the half derivative of Chebyshev polynomials, these weighted Chebyshev polynomials, you get a short-term recurrence in terms of, again, these ultraspherical polynomials. So you again end up with these banded operators, and everything works nicely. Again, I'll gloss over the example, but we can do similar things. So here we looked at what's called the fractional area equation. You might be familiar with the normal area equation. You get these oscillations for positive x and basically flat solution for negative x. Usually that's done with a second derivative here, but here we did this with the 3/2 derivative. Okay, and everything works out nicely. We get roughly 11 digits of accuracy in this. The conditioning isn't perfect in this case for reasons, but it's right. If you get 10 digits, then you're doing pretty well. Again, and I very briefly want to touch on extending these ideas to multiple dimensions. Emma's going to speak next, my PhD student. She's done some work on this. But Dan, myself, and Alex showed how we could do things at multiple dimensions. So even in their original paper, it was shown how to extend the ultraspherical ideas to 2D. You basically take a tensor product expansion, and everything works nicely. But if you want to look at more interesting geometries like this fractal pentagram kind of shape, you need to do something else, right? So typically what people do over here is they do finite difference methods or finite element methods, or maybe spectral element methods, which is more closely related to what we're going to do here. And so what is the spectral element method? Basically, you chop up your domain into smaller pieces. These are usually either quads or triangles. Here I'm just doing it with squares for convenience. And you sort of pick this balance between, well, do I want to break up my domain into smaller and smaller pieces and have low order polynomial approximations on each of the pieces? Or do I want to have sort of larger subdomains, but have a higher order discretization? So that's what they call H. H means the size of my pieces. Do we make that smaller, or do we increase P, make the degree of our polynomial expansions bigger? I won't go into the details because Emma's going to talk about that, but what we showed is that you can use these ultraspherical ideas in this idea of domain decomposition. You can split everything up. It parallelizes very nicely. And we wrote some software, which we called Ultra SEM, which can solve these kind of problems on these very much non-rectangular geometries using these ideas of banded differentiation matrices, exponential convergence. And in fact, in order to solve, I think, this Helmholtz-like problem on this quite interesting geometry, this is all the code you need in MATLAB. And then since then, Dan has extended these ideas so you can solve PDs on surfaces using these ideas. Emma, in her master's project, looked at more interesting geometries with holes in, which she called the Skronot domain. And then just to summarize quickly, Basically, the key ingredients we had here were these banded operators between these different function spaces. If you could derive these using the right spaces, and also these conversion operators, you could end up with these fast spectral methods. So thank you very much.
Any question?
Thank you. Such a nice presentation. My question is that by applying spectral methods, okay, how to resolve the non-linear issues in the problem?
So I glossed over the nonlinear stuff here. Typically, what you would do is you would linearize and use some kind of Newton-Raphson iteration. The price you pay there is that you then have essentially non-constant coefficients that come in, and the degree of those is the same as the degree of your discretization. So you often lose this almost banded structure. So there are some ways around that that are maybe a bit too technical to go into here, but we can talk about that later. So basically, you linearize and use Newton's method would be my summary. If you're doing time-dependent problems, then that's easier. You can do sort of implicit, explicit methods. So then you do the linear part implicitly and the non-linear part explicitly. And again, that allows you to get around the issues.
In the differential equations, there are some derivatives. Okay. So when you apply spectral methods, then how you deal the derivatives, particularly fractional derivatives?
Sorry, I didn't catch the last part.
For example, when you solve a fractional differential equations, then there you have to compute the derivatives while applying spectral methods.
Yeah, so I mean, that was let's quickly go back. Maybe it's him. Maybe I glossed over that too quickly. What we're showing here is that here's the fractional integral, but we showed how we could apply the fractional integral to each of our basis functions, right? And our solution is composed of these basis functions. So we could just apply that term by term.
It's true, but it's not a generic. The reason is that it's a half derivative if you have a 3
Right,
by 2
okay, yeah, I glossed over that too. So if you looked at the title of the paper, it said rational order. And the reason for that is because we need to take this combination of these different terms. We can talk about it later, but you can do arbitrary rational orders. Doing arbitrary fractional orders is a bit more complicated, and this approach doesn't work. So this approach is a little bit limited in that sense.
Okay, thank you. I'm grateful to you.
Thank you.
Any other question? Any question from the online audience? Okay.
Thank you, Prof. I just want to find out what was the motivation for using Riemann-Liouville integral instead of any other fractional integral? And secondly, the convergence and all that, the fractional one, I think is bit, how did you deal with that?
Two questions. One of the reasons we used the Riemann-Liouville was because we were able to find this nice short-term recurrence for the derivative of the basis functions. And in terms of the fractional derivative, both Caputo and Riemann-Liouville work. I think it's the most widely used fractional derivative. I know there are different kinds. And your second question was, how do we deal with the convergence? Yeah, that's a little bit more complicated in the case of the fractional, because here we're taking this combination of these two series expansions. So technically, this doesn't define a basis. It defines what's called a frame, the sort of redundancy in there. We didn't analyze it too much in the paper, so it's probably something still to do. Yeah.
Thank you for the talk. I just want to check if the method it can also work on unstructured meshes.
Unstructured meshes. Is that your question? Yeah. Yes and no. So Emma is going to talk a bit more about PDEs in a moment. And Yes and no. So basically what we do in the PDEs is we break the domain up into these smaller pieces. The method is unstructured on each of those smaller pieces, but there is a global structure. So there's sort of a hierarchy, if that sort of answers your question. So there is some structure to the mesh, but within each of the mesh elements, there is no mesh. I drew these dots here, but those are just informative. So yes and no, which is not a satisfying answer. I'm sorry.
Any other question? Okay, let's say thanks, Professor Nick Hale, for such a wonderful presentation. Our next speaker is Emma Nail. Oh, sorry. So let's thanks Emma for presenting her work. Over to you.
That's mine.
We go. Good.
Stand on the side. All right, almost good afternoon, almost 12 o'clock. Before I get started, I want to ask if anyone knows about the G20 Women Shutdown happening at 12 o'clock. Yeah, well, unfortunately, I'm going to be, yes, it's happening on the rope line. Unfortunately, I am giving my talk. If you want to leave, you're very welcome. I would come with. But I think recognizing that it's happening is my contribution to wanting to be there. All right. To get to my talk, so sorry, the title on the program is fake news. I'm not talking about the game methods. I ended up deciding to talk a bit more on the things Nick introduced today because I thought it would link quite nicely as one topic. So Nick introduced the ultraspherical spectral methods, and I'm going to talk a bit about the spectral element method part of that. And so it might be things at the start might be a little bit repetitive of what Nick introduced, but I'll maybe just recap some of those ideas that I'm going to build on. Right, so there we go. So we're focusing on solving ordinary and partial differential equations, which of course has various applications in a wide variety of fields. And specifically, we're making use of spectral methods to solve these types of equations. And that's because we get really high accuracy solutions from these methods. But the limitations that they have is firstly that they give rise to really dense matrices, and this was a big focus in Nick's talk. And he introduced the ultraspherical spectral method as a way to overcome some of these dense matrices. And in my talk, I'm going to focus a little bit more on the second limitation, which is that they're often restricted to quite irregular domains, and it becomes difficult applying them to more complicated geometries. And so that's what I'm focusing on mainly. So specifically to work in this type of domains, we're going to consider a domain decomposition approach, which is called the hierarchical Poincaré-Steklov method. And along with that, I'll introduce a new domain transformation that I worked in. So this was mainly the work of my master's, and so I'll show you a bit of the results of that. And then the aim is to solve on some more complicated domains, such as that shape we see on the right. So Nick introduced spectral methods, but I'll just run through it again. In Galerkin spectral methods specifically, we express a function as a linear combination of basis function. And so this function is represented by those coefficients, UK, in this linear expansion. And we're looking specifically at Chebyshev polynomials for these basis functions. There's many other choices, but Chebyshev polynomials are really good. It's better than the power series, as Nick demonstrated, and it's got good convergence properties. It's stable, and it has a connection to the fast Fourier transform, which makes it quite effective to compute these coefficients. So They're defined here by their occurrence, or it has an explicit formula for these polynomials as well. So a nice example, Nick showed us for you as well, is how we can solve something like the area equation using our Chebyshev spectral method. And for that, we need to construct this differentiation matrix and also other matrices like multiplication matrices, such as J here. But as Nick explained quite well, is that in our Chebyshev approach, these matrices tend to have this upper triangular type of structure. Just note that this is originally infinite dimensional, where U is the coefficients, a vector containing all of those coefficients. And then here we also incorporate the boundary conditions of the problems into that system by putting them in this matrix B. So we need to find coefficients that satisfy these boundary conditions. And they we usually put at the top of our matrix, and they give us these dense rows that we see there. So on the right, this is just visualization of all the non-zero entries in the system we're solving here. So it's upper triangular, and the goal of Nick's work was to find ways to make that matrix more sparse, or sparse in a way that's more useful for us to improve efficiency. And that was done by introducing the ultraspherical spectral method. This is a Petrov-Galerkin spectral method, so it means that the solution is expressed in one basis, the Chebyshev polynomials in this case, but then derivatives and thus the resulting differential equation is expressed in a different basis, and that's the ultraspherical polynomials. And why the ultraspherical polynomials is quite useful is because they have this very neat connection to the Chebyshev polynomials, and as Nick said, they're actually Chebyshev polynomials of the second kind. And so if we take a derivative, we get to the ultraspherical polynomials, and then also they have a quite neat conversion between these bases. And that's what we use when we try to solve problems like the area equation, now using the ultraspherical method. We again construct our differentiation operator, but it now converts the coefficients from the Chebyshev basis to the ultraspherical basis when we apply it. And so we must ensure that the rest of the equation also gets converted to the ultraspherical basis. And so we make these conversion operators that switch between bases. And similarly for the right-hand side, we must switch to the ultraspherical basis. And again, boundary conditions are incorporated, and the resulting system is a bit nicer. It's closer to a banded shape. We see there on the right. And we also then find that our ultraspherical gives us a bit better accuracy. It's more stable. And if we run it for very large matrices, the execution time tends to be a lot lower because we're solving a more sparse system. Of course, if we use techniques that benefit from the sparsity. This was in one dimension. In 2 dimensions, it works very similarly. And just note this idea of the ultraspherical method was first introduced by Olver and Townsend. And for 2 dimensions, we've got a matrix of coefficients and not a vector anymore. And then when we take derivatives, it only converts one of the Chebyshev polynomials, so x derivatives, keeps our Chebyshev polynomial in terms of y, but it converts our x polynomial into an ultraspherical polynomial, and similarly for y derivatives. So that means when we want to solve something like the Helmholtz equation, that we can post-multiply to get x derivatives, but we must pre-multiply by the conversion operator to make sure that the entire coefficient matrix is in the same ultraspherical basis. And so similarly, here we pre-multiply for y derivatives, but we post-multiply with the conversion operator to get all our coefficients in the same basis. And finally, we can solve the system and plot some nice solutions. Okay, so this all works quite well, but as soon as we try and solve on more complicated domains, we still have problems in terms of accuracy and efficiency of these methods. And so our domain decomposition approach has the 2 goals of, domain decomposition. You just take a larger domain and you break it up into smaller subdomains. And it helps us to solve a larger variety of domains, but also to break down large systems into smaller systems that we can solve more efficiently. And hopefully we can solve more complicated problems on domains such as this one that's quite interesting. So we looked at a specific domain decomposition approach, which was called the hierarchical Poincaré-Steklov method. And this was first introduced by Martinson and then extended in the work by Fortunato, Hale, and Townsend. It works by joining together solutions between subdomains using operators. The first is a solution operator. So this takes in values on the boundary of a domain, and then it computes the local solution inside that domain. The second is a Dirichlet to Neumann operator. This also takes in information on the boundary of a domain and then computes the Neumann data essentially on the boundary. So the derivatives or the outward flux on that domain. And these are the operators we use in our hierarchical scheme to actually get to our solutions. So this HPS method works in 3 stages. The first is the initialization stage. Here we take a big domain and we break it down into smaller subdomains. We refer to them as leaf patches or just leaves. And in this process, we then discretize on each of these leaf patches on their own. Since they're independent in a sense, this can be done in parallel. We then construct the operators, so the solution operator and the Dirichlet to Neumann operator on each of these smaller patches. And this is really a big part of the work to be done in this method. Then the next stage is the build stage. We now have the operators on each of these smaller patches, but we now merge these operators together, or merge the patches together to build a hierarchy from our lowest level up to our global domain. So we first merge patches pairwise, for instance, patch 1 and 2 and 3 and 4 can be merged, and then those can again be merged together to give back the global parent patch. So here we construct the solution operator and the Dirichlet to Neumann operator of each of the parent patches in the process. Once this stage is completed, we can move on to the solve stage. Here we give the boundary conditions of the problem. So up to this point, the algorithm has not had the boundary conditions. It's constructed all of these operators without that. We supplied the boundary conditions, and it will now map this boundary conditions all the way down to our lowest level. So it uses the boundary conditions on the global domain to compute, using its solution operator to compute the data at the interface. That's the red line there. If we know that red line, then we essentially have the boundary data on the next level of domains. Once we have their boundary data, we can use their solution operators to compute their interface data, which is then given to their children. Once we have the boundary conditions of all the leaves or lowest level in the hierarchy, we can use their local solution operators to compute the solution on their domains. Once we have that, we essentially solve the problem. We just put it back into the global domain. So this HPS scheme was implemented into a software system that Nick mentioned, UltraSEM, and it was written by Fortunato, Hale, and Townsend. And so they used the HPS scheme with the ultraspherical spectral method. And this is another implementation of how that can be very easily used to solve problems. Here we're simply solving on a rectangle, so it's not very complicated domain. And we supply the problem. In this form, it's mainly up to second order problems. So we're solving the Helmholtz equation down here, and its coefficients is just given in there. We have a constant right-hand side, but you could put functions in there as well. And then we progress with our 3 stages of the HPS scheme, which is initialization, where we break down the domain to its smaller subdomains and create these operators. Then we build, which means we merge the operators all the way back to the global domain. And finally, we solve, which is we give the boundary conditions and we solve down the hierarchy to the lowest patches. And again, the boundary conditions are only supplied on the very final stage. So once you've run the first 2 stages, we can change the boundary conditions without rerunning the first 2 stages and solve the problem for various different boundary conditions. This is on a rectangle, but UltraSEM has various other shapes built in. It's built up quadrilateral elements and then different shapes made up of quadrilateral elements, such as the triangles and polygons, which is just decomposed into these quads. And then that first fractal shape we saw can also be made up of quadrilaterals. So the goal in my work was to see if we can build in a domain that is not currently in Ultra ACM that has curved boundaries. And I ended up specifically focusing on this shape, which is a square with a circular hole at the center. This ended up being a nice shape for certain engineering applications. If you have a plate with holes in it, perforated plates, calculating the stresses around those holes. And also if you want fluid flow around things like circular obstacles or waves around pillars, this ended up being a nice domain to focus on. I did give it a name as square donut because it looks like a square donut. Each time I talk about this work, I really just want to bring square donuts, but I've never actually found a place that sells them. So I will have to learn to make them myself, I guess. And so the goal was to build this new domain into the Ultra ACM system so that we can solve on problems on this shape. So to do that, I broke this shape into smaller bite-sized pieces. And I named these pieces. A little slice of a square donut is a square nut. And it looks like this. It has parameters that can change, such as the radius of that circle and the height of the domain, and also the position of it. But the angle there at the center remains fixed. And our square nut's essentially a coordinate transformation. So we had to design this algebraic transformation to be able to solve in it. In it, straight lines on a square would map to straight lines on our square nut domain. For vertical lines, for horizontal lines, they map to curves. But the idea was to ensure that if we have equally spaced points on the square, it maps to equally spaced points on the straight edges of the square nut, mainly so we can merge it with other types of shapes that is already built into Ultra ACM. And so we had to transform the equations so that we can map our problem from the square nut to the square and solve there using Ultra ACM, and then map our solution back to our square nut domain. So its implementation in Ultra ACM works very similarly to all the other domains, which means you define the parameters that describes the domain, and then simply construct this Ultra ACM object. You give it the problem, right-hand side, boundary conditions, and again, it follows the steps of the HPS method to initialize, build, and solve. And here in the initialization, it breaks this bigger domain, the square donut, into its little square nuts. We did some tests to see what is the accuracy and how well does this domain perform. So first we did P refinement, which is polynomial refinement. So on each square nut, we increased the degree of the polynomials we used to approximate on it. I did this for 3 different refinement levels. So R equals 0 just means I use the square nuts as is. R equals 1 means I refined the domain once. So I increased the polynomial on each of the little sub-square nuts. And then R equals 2 was another refinement level. In this, we saw that we get exponential convergence, a little bit better for the higher refinement levels, but they take a lot more computational work. So not necessarily worth it in this case, but if you have problems with more complex geometries, such as singularities in the corners, that might become more useful. Then we also considered H refinement, which is refining the domain more and more. So that 1 over H is essentially a way of measuring how many subdomains are you using. And then we kept the polynomial degree constant on each of those elements. And we saw algebraic convergence here, roughly to the order of H to the P minus 1, or N minus 1 in this case. And again, of course, higher polynomial degree did give us better accuracy. Another measurement is to consider HP. Oh, sorry, I'll get to that in a moment. So we just compared what the complexity of the method was that we implemented to what we expected it theoretically to be. We didn't expect it to be much different to the implementation on rectangular or quadrilateral elements. We did see a factor higher in these orders, but the orders themselves were the same. And the higher constant that we see is due to the nonlinearity in the derivatives we introduced on this new domain. So we see that our initialization stage is taking the most of our computational time into the fore versus build and solve stages, which are much quicker. And this again means that to solve the problem on many different boundary conditions is quite inexpensive, that initializing and creating those first operators does take the most computational time. And then similarly for our H refinement, we saw the kind of same rate of increase for all three of them, but again, initialization taking the most time. So on HP refinement, in general, it is nice to find a good type of trend for refining both the domain and the polynomial degree, but it is a quite complex problem. We saw super algebraic trend here in terms of our flop count. So that's our number of operations, which would count both for increasing our number of subdomains and increasing our polynomial degree. But we couldn't get any type of general trend. This was just for this specific example. We just tried various different examples on this domain, and a nice one was Berger's equation, which models the flow of shallow water in certain circumstances, also used in shock waves, turbulence, mass transport, acoustic transmission. So it's the system of PDEs there. And we used a quite simple implicit, explicit finite difference scheme for the time, but then our spectral method for space. And the domain we used here consisted of 3 square donuts. So this merging all of these square nuts with some square rectangular domains. And we got a nice solution of it, modeling the fluid flow past a collection of pillars. There's various extensions that can still be done to this work on some non-uniform refinement schemes. These are some examples that was used by Fortunato, Hale, and Townsend, which is quite nice if you want to refine into corners, if you have some singularities or very things changing a lot there, or if you have points at the center of domain that you want to refine around. Other schemes can also refine into corners, but the problem is that you might have hanging nodes, which is when you have nodes on this in between of the boundary, but the shape you merge with this might not have domains at matching exactly those points. So these ones are much nicer for being able to match domains. We didn't use very sophisticated time discretization, so that's a very natural extension to this. Other coordinate mappings, and as Nick also mentioned, Fortunato had quite nice extension to surfaces, which used a more general mapping from a square to a surface element, and he solved on quite interesting shapes, like little cows. Okay, that is it for me. Thank you, guys.
Any question from the audience? I just want to mention I'm the strict session of the chair for the Doodles session because everyone is ending at time, even before time. Maybe everyone is taking my time very serious.
I knew everyone would want some lunch, so
yeah, maybe. So no question. Oh, one question.
Thank you, such a wonderful presentation. Actually, it is indeed some novel results are there. My question is that the problem that you solved, all the problems can be solved by using Chebyshev polynomials. Okay.
Say again,
the problems that you solve, these problems are solvable by using Chebyshev polynomials.
On the regular domains.
But
yes,
you inserted the ultra-spherical polynomials.
Yes.
What was the special reason to, if the study can be done with only Chebyshev, then what's the special reason to use ultra-spherical polynomials?
To transfer to the, so we are still using Chebyshev polynomials to solve. Even in the ultraspherical spectral method, we're converting to ultraspherical, so your equation gets converted, but the coefficients you find are still Chebyshev coefficients. I guess that's the difference between the Galerkin method, which is just Chebyshev, the basis for the solution, and the differential equation, but now we're switching. So now we're using both Chebyshev and ultraspherical. And this was very much a big focus in Nick's talk, is that by switching the relationship between the derivative, that expansion, and the expansion of the function or the solution, it's a much simpler relationship that you get that one-to-one, that one term when you calculate the derivative. I added here, and I think Nick summarized it quite well, is that you only have one term there. You don't have multiple terms. And what that means is that in this matrix, it means that this bandwidth of that entries are smaller by switching to ultraspherical. Otherwise, you'd have a lot more entries in that matrix.
If you also check the result by changing the source term, the different source term.
What do you mean with source terms?
The differential equation, the source term is that makes the equation informal.
The source term in the, sorry. Oh yeah? Yes.
In the homogeneous, so
yes.
we changing the source term, polynomial, uniform equation time to time.
Yeah.
If you check the result by changing different source terms.
Yeah, so I guess all the other terms here would influence how thick that bandwidth is, but we know that for the ultraspherical method, it's a bandwidth, but with Chebyshev on its own, it's upper triangular. Yeah. So these terms would influence the thickness of that diagonal band, but it will still have a bandwidth instead of being full with entries at the top. Yeah. Yes. Oh, yeah. So later I just use a constant value, but you could use, it could be functions, and we still have better solutions for solving better convergence and stability.
So I'm an engineer, so I thought the approach to create this element with a hole in it is actually really, really clever, because there are lots of holes in engineering, right?
In engineering,
or in structures, Well, you have to put the bolts in somewhere, but as a chemical engineer, if you've got a plate, there are holes that the it drains through, etc. But it's so clever. In fact, my question is, like, why haven't the big simulation companies like ANSYS and COMSOL and all these guys, why haven't they developed these quite unique elements, which I think would work really, really well? So traditionally, if we do finite element or finite volume, you'll just have to take your square elements or your tetrahedrons and make them really small. Scale them quite small. But the other reason that you scale them so that you have these tiny elements around the circle is because the gradients tend to be really high right around these circles, which would be tubes and heat exchangers or that kind of thing. So do you think your method is able to handle steeper gradients with fewer elements as compared to like finite? So it's in two parts, so why isn't ANSYS doing it, and how would your method handle very steep gradients?
Thank you so much. So I definitely have less experience with ANSYS Fluent or any of the other engineering programming. I guess in general, spectral methods are just really hard to adapt to different scenarios. Of course, I did a nice little element here, but it's very specific for this one. If you want to design general software, it gets harder and harder adapting the spectral method to each scenario. So I would definitely think that's one of the reasons why these much bigger software programs don't always focus on spectral methods. Whether it would be better, I guess our other goal is getting really good accuracy versus often finite element methods get a lower accuracy, but you can refine, you have a lot of flexibility in refining these types of things and merging a lot of shapes where we have a lot less of that, but we get better accuracy. I don't know if it would do. I think it would be problem specific. I definitely tried some scenarios which didn't work on the shape, but a lot of times I was unsure whether the boundary conditions I was using is super sensible. I think it would be more sensitive to the type of how you define that problem and how you give it the boundary conditions. So
one comment from my side. So it was nice presentation. Each slide and each step was elaborated in a very nice way. You guys are doing a wonderful job. So
thank you so much, Ollie.
You have one more question.
You have time.
Okay.
There's no time, it's lunch.
Yeah.
Actually, I was wondering about one thing that by applying spectral methods, they always provide us exponential convergence. Okay.
That's the goal, at least.
Okay. So here there you did a domain decomposition, and we did domain decomposition when you are feeling difficulty in finding the convergence in one region and not the other region. So if they already provided exponential convergence, then why the domain decomposition? What's the role of decomposition? Domain decomposition is there. Is some type of convergence issues or some discontinuities issues? What kind of?
So I guess with the domain, we wouldn't be able to solve on that circular domain using a spectral method if we don't decompose. I guess designing a mapping to that domain with a hole would be quite hard on its own. So the decomposition is very important for the domain there. In terms of sorry, you asked about why we decompose if we already get them. Yes. I guess the other part is that with this HPS scheme, we also break it into the elements which are independent of each other, so we can parallelize. So it's not so much about accuracy, but more about speed and efficiency. Yes.
Let's thank Emma for such a wonderful presentation. So now we have two presentation after the lunch. So we will join again at 1:30. Yeah. Okay. Hello, Professor Bega. Can you hear us? Professor Anas, can you hear us? Are you here?
Yes, yes. Is it Ali?
Hi.
Hi, hi. How are you? Can you
Hi,
hear
how
me?
are you? Welcome, Professor. We are just waiting for the audience to come back in the and settle all in the room, and then we will means ask for you to present.
Okay, thank
Okay.
you.
So
Did you
just
see
give
my
us
last email to
just
you?
so yeah, you can share your slides from your computer.
Actually, that was what I requested. I requested that you share it. I would speak through it, and I would ask you to possibly, if I need you to change the slide, I will let you know. Check my last email before you actually check my last email before you share it, because I did say you can add
Wait.
your name. You can add your name and Prof Moyo's name, because I'm going to speak on our behalf.
Professor, just wait because volume is too low here. I am not able to hear you. Can you say it again?
Okay, I said do check my last email. I sent you an email to say you can add your name and Prof Moyo, because I'm going to speak on our behalf. Check my last email I sent to you.
He's asking you to check his last email that he sent you.
Okay. 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 I will add. Okay. Sure.
Yes.
Sure.
Yeah,
I just
do
yes.
that.
Thank.
Do that, and you will scroll, and I'll tell you which page to move on. I'm going to speak on our behalf. Okay.
Okay. Okay. Okay.
Good. Good.
Okay.
By the way, how many minutes do I have?
Sorry.
How many minutes do I have?
I think, Professor, you have 25 minutes.
Oh, good, good. Please do me a favor.
Yeah,
When
20
it's
minutes.
about
Yeah, 20 minutes from 1:30 to 1:50. So you have 20 minutes.
okay, when is 1:15, you tell me, okay?
Yes, yes.
When is five
I
minutes
will.
to time, you tell me, so that I wrap up.
Yes.
Yeah, I don't know what's going on here anymore. You
Okay.
just wanted
Okay. I will handle it. Thank you. Thank you.
You also do grays.
Yeah.
Okay.
Yeah. Thanks.
Yeah. No, I certainly would have done it. But
Yes, yeah.
I'm sad we don't really know what's going on.
Okay. Okay. Thank you. Again, Professor Enes, can you speak again, because the volume here is very low. Because if you speak near the mic, it will be most means.
Okay. Can you hear me? Can you hear me now?
Yes, now it's better. It's much better now.
It's much better now. Okay, what I said then is add your name and Prof Moyo's name on the slide, the authors, because I'm speaking on our behalf.
Yes, exactly. Yes.
And
So
then
yeah,
I
you
would like you to scroll through each slide. I'll keep giving you directions, and you keep scrolling if there's a need. Yeah, and when it's 5 minutes to time, because there's a lot that I would love to say, but I don't think I'll get the time to do that. When it's 5 minutes to time, you tell me and I'll stop, and I'll wrap up.
okay. So now you want me to add our name on the slides, and you want me to share the slides from
The
here.
author, the author, where my
Okay.
name is, it is me, it is you, it is Prof Moyo. It's just the work we're doing. I'm going to speak on our behalf. I thought you would have added it initially when we spoke earlier on.
Okay. Let me share the slides. Okay.
Yeah, share the slide and add our names and share the slides.
Okay. Okay, Professor. Now you can. Okay, so let me introduce you. We have Professor Enes with us. He's from Stellenbosch University, and he will be presenting explainable models for dynamical system in STEM. So this work is in progress. So we will present concept and early scan. Professor Enes, it's over to you now.
Okay, thank you very much, colleagues. I appreciate it. Ali, I would say sorry to you. Apologize to not just you and Prof. Moyo, but also to the audience. That is because I'm actually out of town. I went to Cape Town, or what is it, Johannesburg, to also be part of this forum, and I had to travel somewhere else. So I know you were eager, you wanted me to be there physically, but unfortunately, too many things to get done within this short period, and marking and so many things. Colleagues, I appreciate it for coming also to listen to our work. This work is not just the work I'm doing, it's the work that we are doing. You would see Ali is there and Prof. Moyo is also there. His work is ongoing work that we're doing. There's a lot that honestly I would love to speak through this, but I do know that I won't have the space and time to complete it. So I'll leave some of them in terms of questions or queries if you do want me to do that. That is the first housekeeping. The second housekeeping is that it's not my normal way of doing things. I'll be speaking quite fast, but I'll try to ensure that the important parts of what I need to say is captured. And then we take it in terms of questions and comments. So as I said, the title here, Ali, let's stick to slide 1. So we're speaking about explainable models for dynamical systems in STEM. And STEM over here, we're speaking about science, technology, engineering. So it would, most of what we'll be talking about as work in progress we hope that it will be applicable in any of the sciences that we do. So it's not specifically for any particular work, but knowing that majority of us, particularly myself, Prof. Moyo and Ali, we are specifically into maths, but we're drawing heavily on neural networks. And I greet you all wherever you are, whether online or physically. Good morning, good afternoon to you. I'm going to unpack the title for us to probably build on that. So essentially, we can build small models that I've also indicated that this is actually ongoing project. This ongoing project is not something we have completed. We can build small models that, 1, predict how a system changes over time, and 2, give clear rule, consistent explanations that mathematicians and educators can actually trust. And that's our goal, eventually, what we are planning to do when we started looking at this work. To do this, I think the best thing one of the things we hope that we can use to make it much simpler for us to understand is to sort of keep it simple and anchor on simple experiments that cuts across, whether you are in math, physics, you are in chemistry, or you are in any of the STEM, you should easily be able to understand. We're using examples such as simple familiar examples such as pendulum, water tank, predator, pre-system, and they are deliberate. They are deliberately chosen such that you are familiar with these things. And sort of, I would also try to move through 4 points. And the 4 points I would love to move through would include why explainability is tricky for dynamical systems when we speak about explainability and dynamical systems. And secondly, small neural symbolic pipeline. I would also speak to 2 concrete examples with equations if there's opportunity, how we plan to evaluate these. As I said, this work is more of work in progress. Ali, can we go on to slide 2? If I'm very fast, and I'm gonna use you as a litmus paper, Ali. If I'm very fast, please do let me know so that I would slow down a bit. So slide 2, basically what we hope to do given that this is ongoing work, is the question is, why care about explainability here? Why care about explainability here? In terms of when you look at the title, let me start with this kind of motivation. In our domains, we just don't trust when we say 90%, we want 90% or 98% accuracy. We just don't trust it. A number of things you and I as mathematicians, mathematics educators, STEM STEM enthusiasts we want to know. One would include something like which term, for instance, is responsible for damping. Remember, I've mentioned pendulum already, right? So if we want 98% accuracy, obviously there should be some form of damping. So which term is possibly causing that damping? For instance, which parameter drives oscillation? We also want to know that. For instance, also another typical example in the familiar case I gave was that whether energy, mass, or population behave in physical sensitive way. I mean, those are some of the things you want to know. And if you look at it from teaching perspective, I'm typical slash teacher slash a researcher in the university. In teaching, this is even sharper. We constantly move students between graphs, right? Equations, right? And verbal explanations. So a useful model should support questions such as if we say double check, double the mass, what happens to oscillation? If pre-production or pre-reproduction or pre-reproduce faster, how does the cycle probably change? Finally, many of our labs are, hello?
Yes, we can hear you. Yeah.
Okay, good. Finally, many of our labs are, for instance, data scarce, and that has been one of the goals of what Ali and I and the DVC sort of we hope to look at. How to actually work with limited data scarcity, but then generate a very good model that respects the rules and regulations of any of such scarce data. So what I'm trying to say is that many of our labs are, for instance, data scarce. And in short, what that means is that we have short experiments, we have few sensors, we sometimes no big data luxury. You and I don't have it. So we want small explainable models that would work with limited data, but still stay aligned with basic rules that I've mentioned, whether in the lab, in teaching, in modeling, or any of the neural networks that we might be thinking of. Ali, can we go to slide 3? I hope I'm doing well with time and not rushing. Speaking. Yes, good. So slide 3 really looks at what's missing in current practice, what is missing in current practice, and what is motivating the three of us and in fact a few other people to say let's embark on this kind of research. And so I'm going to take us through it quickly. I mean, from practice and in research, I've also laid the foundation that we're dealing with data scarcity. So let's shift our focus just a little bit. Deep models, for instance, for time series, for instance, are now quite powerful. A number of us who are into machine learning and deep learning are very aware of that. But in our setting, they have 4 problems. When we speak about deep models. The first one is opaque reasoning. And what do I mean by opaque reasoning? We get good prediction, but weak insight into why the model behaves as it does. When you look at a number of the deep learning models. The second thing is post hoc explanations ignore physics. What does that mean? In simple terms, we're talking about so these saliency maps of feature importance in some instances can point to variables in ways that break down the constraints like conservation or bounds. The third one is generally what is motivating us. What we kind of one is dubbing as data hunger. And what we mean by data hunger? Data hunger in this sense speaks to many architectures that sort of assume long histories and dense sampling. That's really not our typical classroom or lab setting. And the last one is weak integration with formal maths. And to expand on that, essentially what we're saying is that pattern recognition, for instance, is not properly tied to equations and invariance that we rely on for understanding. So essentially, when you look at these four gaps, 4 issues, 4 problems, the question we ask is that, can we design a small pipeline where a neural component learns from data? That is key. We are not the only one actually doing that. A number of folks have noticed that data scarcity and modeling with data scarcity is becoming serious. So that question is very key. The second question is that the second question we then pose out of these 4 gaps is a symbolic component gives back. Would we be able to do that? Can we design a small pipeline where a symbolic component, right, gives back short equations? And lastly, a rule layer checks whether we can design a small pipeline where a rule layer checks that those equations behave reasonably. And I think we don't have to go too far for us to actually realize that these 3 questions are fundamentally the key reasons why I'm not into that field and I don't do that. Those of you who are familiar with Navier-Stokes equation, if you look at the last 2 reasons, particularly the last one, can we design a small pipeline where it's a rule layer kind of checks that those equations behave? That probably would have been the reason why up-to-date Navier-Stokes equation becomes quite problematic issue. The 4th slide, Ali, if you're listening to me, let's move on to 4th slide. I'll take you through quickly. The 4th slide, essentially, what I would want to espouse on is to speak about a small neural symbolic pipeline. Remember, we indicated that this is work in progress. In fact, is within the idealization stage. We're still idealizing around it, putting together the blueprints, making sense of what we want to do. So one of the things we probably would test would be hoping to test is actually a small neural symbolic pipeline. And so I'm just taking an example. Unfortunately, I'm just taking an example. So for the pipeline in 3 pieces, let's say neural, symbolic, and rules, there are a number of things we might have to consider. Unfortunately, because of time, I might not be able to fully capture all of it. But the first one basically is data and neural approximation. It's key. There are a number of things that I would have loved to speak through that. And I think in terms of small neural symbolic pipeline, the first, which is data and neural approximation, would have been speaking about small time series type of data sets. Ali, unbeknownst to you and Prof. Moyo, I sort of tried to put together an example using pendulum, but I'm not able to share that with you. In case maybe once after this session, I'll share it with you and give you an idea as to how we could have used pendulum or rates of change to do that. And those of you colleagues who wish to pursue that, you can also pursue that. I think the second aspect is also symbolic step. And when I speak about symbolic step or back to equations, basically what we hope to achieve by that or explore further would be we sort of apply symbolic regression on learned functions to sort of recover short formulas. That's essentially basically what we mean. So for instance, if we have a simple equation, sort of differentiate a particular variable with respect to, say, time, and that approximates to a particular function. How do we do that? Rather than, say, a dense neural network, because remember, we're dealing with scarce data. All right. The third aspect, and then I'll move on to the 5th slide, would be one of the things in this particular aspect would also be the rule layer. Basically, Ali, thanks for actually moving on to this particular slide. This particular slide is an illustration of everything that I've just said. It's an illustration of everything in diagrammatic form. I just put it across for those of you who will be looking at it. Anyhow, the rule layer aspect of it, we hope to put together would include constraints and checks. because remember again, we'll be dealing with scarce data. So we will be,
Professor Enes, we
yes.
have you have 2 minutes to conclude your presentation.
Wonderful. Okay. So one of the components will be rule layer, or that is constraints and checks. And that would include to be encode simple and interpretable rules. A number of rules we have to be cautious of. That slide you are showing there summarizes some of the things that I would have, I mean, we're hoping that would be looking at. And essentially, those are some of the things that we will be looking at. Ali, if you can go to the last slide, I think I can jump most of these things that I need to say and go to the last slide, slide 7, probably slide 7, because the other slides are just examples that one will be considering. So slide 7, evaluation and closing. Basically, what we would love you to understand from all of this as ongoing research in terms of the topic would be how we will judge these models. To close, I mean, these are a few steps that we consider or would consider how we intend to evaluate these type of models in terms of dealing with scarce data. One will be rule keeping, and then the second one will be equation mapping or equation matching. The third will be what if sanity type of checks. Those of us who get more into machine learning, we do a lot of sanity checks. So that's one of the things we'll be doing a lot in what if sanity checks. And of course, the last one would be transfer potential. I can tell you for a fact that I have expanded on this. When we say rule keeping, what are some of the basic architecture in terms of rule checking or rule keeping? We have noted that. I'll leave it to you as questions. When you raise it, I'll respond to that. When we say equation match, what are some of the basic things that we would have considered under equation match? A few things we've alluded, we've pointed that out. When we speak about what if sanity checks, there are a few things we hope to keep in mind when doing what if sanity checks. And lastly, when we speak about transfer potential, what would we be considering when we speak about transfer potential? There are a few, I can tell you for a fact that there are a few things that have been pointed out, which we can consider both in practice and in theory. But due to time, and I said there's so much that has to be done in this, and this is exploratory. This is still under, is ongoing. I'm going to leave it at that. If it comes up as questions, Ali, don't worry, I'll keep that. I'll try to see if I can resolve that for us. Thank you, colleagues. I appreciate it, and thanks for listening.
Okay. Thank you very much, Professor Enes, for such a wonderful presentation. We have any questions from the online audience? Okay, so we have a question from Professor Andronikos.
Hello, Anas. Thank you for the talk. I enjoy it. I have actually a small comment on this last slide, as you can see. I mean, on the test that you want to do. So, I mean, okay, it's necessary to do the equation match. I totally agree with you. But if you do that, it's not necessary to do the rule keeping test. Since, for instance, the invariance or any rule that you get already should satisfy the equation from where you generate the rules. So they should be there. That's a way, I mean, to avoid the extra steps. That's a suggestion. And regarding the transfer problem that you mentioned, that is a, I mean, Ali will tell you probably for sure it's called like, for instance, if you want to have a specific algebra to determine all the systems that applied algebra like that. So that will give you a family of models that you can train, but not necessarily will give you the exact equation that you want. So it is a hit, it's related to the one, but it's not exactly something that will fix you the real world application directly.
Okay. Thank you very much, Professor. Look, Ali, please keep what Professor has just said in mind in case the next time we meet with Professor Moyo, we would keep all of this in mind. Yes, I think you are right. At the moment, it's just exploratory. We in terms of checking ourselves, I see this as health check. Some of these things we may not apply it, we may not really get deeper into it, but I am appreciative of the fact that you are also pointing that out. In fact, initially when I put that on, I questioned myself, would it not be overkill? That was a question I put forward. But I think now you have confirmed my hunch that it might be an overkill. So Ali, keep that in mind, and then when we meet discussing these things with Prof. Moyo and a few colleagues, would know that, I mean, some of the things we need to do and not to do, particularly with the point Prof raised and also the transfer. Thank you very much. I appreciate it.
Something else, I almost forgot it. So actually, it's my suggestion is the following. Take the invariants, for instance, the rules that you determine from the equation, and try to use them to solve the problem, instead to verify if the solution of the problem that you found satisfies the rules. I mean, that is actually that you want to use what you can analytically to solve the solution. I mean, to use the analytical technique you have to go in your approach.
Good. No, that's fine. That's really welcome. I must say that some of these things are put there, though we indicating that they are for the ongoing research, but also specifically for this particular presentation. But I'm happy that I've sort of tested the idea with you and it's received this kind of comment. So we really appreciate that. Your comments are really welcome. And like I'm saying, Ali, keep notice of some of these comments, and if you can write them down at a later stage, when we meet later separately in our research group, we'll discuss some of these things. But thank you, Professor. I really appreciate it. We do appreciate it. We appreciate it.
Okay, okay, Professor. Thank you very much for your such a nice presentation. I will note these things and we will discuss later. Right? Yeah.
Okay, thank you very much,
so,
Ali.
yeah.
Yes, I appreciate it. Keep well, eh?
Yes.
Yes.
Our next speaker is Dr. Gray Manicom from School of Data Science, Stellenbosch University. Please welcome Dr. Gray. Thank you.
Cool. It's not presentable. Share this screen. All right. Thank you very much for having me for the last session of today. Congratulations. You all made it to Friday afternoon. I have the unenviable task of being here and also seeing my font jumping out of the box. I'm not sure how that happened, but I guess these sorts of things are inevitable. Yesterday, when I was practicing my presentation, I saw that it kind of ended on this slide full of equations. And I thought this maybe was going to be a bit too technical for Friday afternoon. Especially based on yesterday's talks that were all quite technical, but today's talks have actually been a bit high level. But either way, I changed my slides. I put on my Friday pants. Instead, I'm going to have a bit of a higher level talk about thinking about heteroclinic networks as computational kind of controllers. And I wanted to begin by looking at actual neural activity to talk about the dynamics we observe in neural activity that can then be translated into heteroclinic networks, and then describing why heteroclinic networks have been used both for human cognition and for AI systems. And then also looking at some kind of future research that I'm interested in doing actually with animal cognition. So starting with this, which is animal cognition, these are the measurements from a mouse that's busy, or a rat, busy tasting different types of food. And we're measuring the neural activity of individual neurons that activate in response to different flavors. So when they eat sugary things, that's kind of column A. And we see that we have pegs and 10 different neurons shown at the bottom. So right at the beginning, you see the firing rate picks up in neuron number 3. That's at the bottom left, when the rat is tasting something sweet. And then you get a different pattern of neural activity where 3 keeps firing, but you can see neuron 9 fires a little bit. And then there's a new pattern of neural activity where neuron 4 becomes very prominent, and then you get a final stage of activity when neuron 9 is firing a lot. And that's what the rat experiences when they're tasting something sweet. So there's a kind of process for the experience of the sweetness, and that changes as the rat tastes different things. Of those, so these are the same 10 neurons being measured in all of these experiments, and you can see that each neuron is responding to different flavor profiles. What we then show in lines A and B is the kind of average firing rate. So we look at, say, the first slice in the bottom left of C, and we say we've got one pattern of activity where neuron number 3 is firing a lot, and basically nothing else is firing, and we call that a brain state. So we say this is a kind of stable state that we see in our system, and while it's active, we call that state number 1, and then we see it switches to a new state. And we do this for all of these. And so what you then see is that you have these kind of intermittent switching patterns where one state appears stable for some amount of time, and then there's a rapid transition to a new state. So this kind of behavior is a key characteristic of neural systems in general, and some artificial cognitive systems as well. But in our brains, in animal brains, this is typically the pattern you see. If we look at live MRI scans and you put it in a video sequence, what you'll typically see is one pattern appears, and then there's a rapid transition to a new pattern that appears stable for a certain amount of time, and then another rapid transition. Another feature that I'd like to highlight here is what we call winnerless competition, which is essentially that you never reach a long-term steady state. So pattern 1, when tasting sugar, will transition to pattern 2. So 2 beats 1. 2 then becomes 3. 3 beats 2. 3 becomes 4, and then 4 will go back to 1. And so you have winners, but they're only temporary. And so the competition, this is also something that pops up a lot in population dynamics, where you have one population, let's say lions eat zebras, but then if there's too few zebras, then the lion population goes down. Or rock, paper, scissors kind of processes where you have cycles. And so with population dynamics, when the lion's population goes down, what that typically means is another species moves in. That species then does well. Then the lions come back because they beat that species. And then the zebras come back, and so on and so forth. So there's never a long-term winner. Another very interesting thing that you'll observe here is that if you look at, and I'm just going to point for those on the screen, it's the third column at the bottom, you see a pattern 1, 2, 3, 4, 1, 4. And so for whatever reason, this rat, when tasting citric acid, because those 4 different rows, they are the different rats, one of the rats switches to the 1 profile, just for a very short amount of time, but they're between 3 and 4, and none of the other rats experience that. What this kind of thing, also quite common in cognitive systems in general, is that you need a kind of robust structure, but where that is actually sensitive to perturbations. So somehow, if you're thinking about this as a dynamical system, you need a kind of robustness, but also a sensitivity, which is quite difficult, at least conceptually, to achieve. And this is now going to bring me to heteroclinic networks and cycles. So I'm going to start by introducing them, and then I'm going to come back to these as computational devices. So what are heteroclinic cycles and networks? Beginning with heteroclinic cycles, these are objects we find within dynamical systems, so within systems of ordinary differential equations, where you have certain invariant sets or invariant objects. Now, they can be anything. They can be periodic orbits. They can be heteroclinic cycles themselves, because heteroclinic cycles are invariant. But for the sake of this talk, everyone I'm going to show you is just going to be a saddle equilibrium. So we have some equilibria, and these are connected with what we call heteroclinic trajectories. And heteroclinic trajectories, if you're thinking about saddles, basically connect the unstable manifold of one saddle with the stable manifold of another saddle. And while this type of connection is typically not robust to small perturbations, because a saddle will have often a one-dimensional unstable manifold and a one-dimensional stable manifold, so they'll just miss each other if you change the parameters even a small amount. In certain contexts and in a lot of physical systems, you actually get invariant planes in which, or invariant subspaces in which these connections are robust. And so they'll always connect. A typical time series, if you have an attractive heteroclinic cycle, looks something like this, where you have a trajectory maybe starting kind of in the middle, and it gets closer and closer to the heteroclinic cycle. And it'll follow the heteroclinic connections, but when it's close to an equilibrium, obviously the dynamics slow down. And so the trajectory slow down. And with every successive loop, the residence time, the time spent near a saddle equilibrium, becomes longer and longer as it gets closer and closer to the network or the cycle. And a network is just a combination of cycles. So at some point, in this case, at the x1 equilibrium, you can either go left or you can go right. And so these cycles are connected together, and you kind of need to make decisions and have transition probabilities. Now, the interesting thing and a key feature of these is, in the previous slide, I showed that the time series gets longer and longer as you get closer and closer. But as you add noise, there's only so far, you can only get so close to your heteroclinic cycle or your heteroclinic network, because the noise is keeping you a kind of distance away. And so what you then get is you still maintain these relatively quick transitions between these metastable states, but you never get that close. So the metastable states don't increase in their residence times as you let the system run to infinity. And so instead, what you get is kind of these average residence times that depend on the noise perturbation magnitudes. Thanks. And we can represent these networks in different ways, as directed graphs or as stochastic processes. Now, I'm going to focus on the kind of stochastic process picture, where we have different cycles and you can switch between these different cycles, but this is just going to change your stochastic process. Now, importantly, we can think of these stochastic processes. Typically, the literature is on Markovian stochastic processes with heteroclinic networks, but they have very, very interesting non-Markovian processes as well. So you can look at the transition probabilities and the residence times, and what you observe is that local interactions near a saddle determine long-term global properties of your network, which is typical of non-Markovian processes in general. And I've got a paper published on that in last year. So going back to our computational devices, what can we do with this information? Here's an example of something hunting. And what we see on the right of the image is, again, the neural activations. And again, we see these kind of activations where you see a pattern of neural firing activity be stable for some amount of time. And we can then represent that as a directed graph, which is the image on the right, on the left. So that's a directed graph indicating the transitions between neuron firing rates, where neurons are firing quite actively. And that then represents a heteroclinic network. Now, again, features of the heteroclinic network then match those features I was talking about earlier. We have metastable states or intermittent states with quick transitions between them. we have a robust network structure that's sensitive to perturbations, because a small perturbation can take you over one of the invariant subspaces. In other words, from one side of a heteroclinic connection to the other. And then you get the sorts of transitions we saw earlier where we had 1, 2, 3, 1, 4. And we also typically have winnerless competition as the key dynamic. This has also been applied in robotics. So this is a colleague of mine from Auckland University did this research. Here we have a reinforcement learning robot. So the picture at the top is a little robot, and it's trying to catch circles and run away from squares that fall down the screen. It has these 7 sensors that are pointing out, and they need to pick up both the shape and the location and the velocity of the object as it moves through time, and the sensors pick up this. So it needs to figure out if it needs to run away or catch it. And this is then modeled, this decision process is modeled with a heteroclinic network. So that's shown at the bottom. Bottom right, you can see the kind of how it makes decisions. It's got 3 states for movement. It can either go right fast, fast, or left slowly. And basically you transition between these metastable states as the thing drops down and it picks that up in the sensors. So it's updating its eigenvalues through a reinforcement learning process. This kind of, the exciting thing for me with this research is that I think there's a kind of generalizable approach here, where we can take an arbitrary stochastic process, we can represent it as a directed graph. We have already techniques to take a directed graph and to construct a system of ordinary differential equations that contain a heteroclinic network matching that directed graph. But we only can do this for the Markovian processes currently. If we then know what the residence times are for that stochastic process, we can determine the transition probabilities, we have the residence times, and we can construct a system of ODEs containing a heteroclinic network that match and mirror those transition probabilities and residence times. The literature is mostly there in the Markovian case, but it hasn't been all pulled together. And for the non-Markovian case, there are still quite open questions. And the AI component of this would be learning the parameters, learning the eigenvalues. So as one research project, I have this research proposal got started but never finished. This is for pigeons. So pigeons pecking different keys. And for the sake of time, I can't go too much into it, but essentially what you're seeing on the left is the average amount of time pigeons are pecking different keys, so buttons that give them food at different rates. So the most popular key is the one at the top, and it gives 27 times the amount of food as the least popular key. But if the environment changes, so sometimes these probabilities, these reward rates switch. So it's not in the pigeon's favor to get stuck just on the most popular key. They need to kind of explore the other options. Now we can model this as a heteroclinic network, but the key thing here from a mathematical dynamical systems perspective is doing this in a totally generalized way, where this could be applied to any type of data. So where you have your dynamics, we know the residence times, we know the switching probabilities, we can write this as a stochastic process. We draw a nice directed graph like that one over there. We couple it to the reinforcer, which changes due to the environment. So we just have a coupled network, but the inter-network dynamics can be learned in a completely kind of generalizable way with a machine learning approach to actually find the eigenvalues and tune them to the residence times and transition probabilities. As I said, for Markovian processes, we're pretty much there with this, but for non-Markovian processes, the local dynamics interact in such a way that it becomes a lot more complicated. But my hope is that this is possible because the long Markovian processes are really key to modeling cognitive dynamics. We need ways of keeping track of the states we've been past in the past. And that's it for my talk. Any questions?
Thank you very much, Dr. Gay, for such a nice presentation. Any question?
Thanks. I mean, some of your slides could open also some new perspective for me, but just to make sure, with my colleagues, we have done quite a lot of work on, for example, transport or diffusion on directed networks. And I mean, our direction was actually to prove that, for example, for fast diffusion, you know, in the limit you obtain ODEs, essentially with right-hand side given by adjacency, I think, matrix of the graph. So do you have something similar here, or it's completely different way of reconstructing ODE from directed graph?
I think the standard approach here is quite different. If I go back to this image, so this, I say it hasn't shown up, this heteroclinic network shown here gives the key idea away somewhat in the sense that you actually end up with two different types of variables. So it's not the most elegant approach. It's a bit forced because you might have your p variables, which could represent something physical in the system, but then you kind of artificially induce these y variables that just are heteroclinic connections. So basically when if y6 is 1 or large, all the other y values will be small, and y moving from 0 to 1 will be following this heteroclinic connection. So the kind of construction approach here is very much from a directed graph. You're creating a dynamical system where your original variables have, let's say, some sort of physical meaning, where if P3 is 1 and your other P's are 0, then you're near a state that might mean something. But your connections here are induced. There are other approaches to how you construct the ODEs, but it's kind of, let's say, a bit brute force. So I think with diffusion models, I think you're really getting it from a more kind of first principles approach. Yes, I'll send you the paper that was used in this case. Yeah. There's two very good papers. One is strictly heteroclinic networks, and one is mixed heteroclinic and excitable networks, because one thing you can consider doing is not having heteroclinic connections, but excitable connections. Because you still have noise, you're going to spend longer there, and you could get stuck there, but the dynamics basically change when these become saddles with small basins of attraction, sinks with small basins of attraction, as opposed to saddles where you know you're going to eventually escape. Yeah.
Thanks for your talk. Just out of curiosity, you're showing the mouse brains, they cycle through like 4 different states. How quickly does that happen?
It does say on the graph, I can't remember off the top of my head, I think it's microseconds.
Like all the cycles happen in a micro.
No, this is 1 second actually. So this is maybe 3 or 4 seconds.
Okay.
Yeah, it's not that slow. So you can think of it as, initial taste, middle taste, and aftertaste.
Thanks.
Yeah.
Okay. Maybe just a follow-up question also on this, and I think I'm quite curious to know how one thinks about or defines ahead of time what the states should be for this problem. For the other problems, it kind of makes sense with the sort of cartpole or the bird, but yeah, I'm quite curious to know, how does one define the states? And could you define the states in a way such that all the rats who eat the middle column behaves?
So the states, depending on the research question, kind of just get defined appropriately. So in my PhD research, I dealt with task switching. So there the states were very, very abstract because with task switching, you're interested in the dynamics of switching from one cognitive process to another, but the cognitive processes themselves are super undefined. And because we weren't interested in the quantitative dynamics, just the qualitative ones, we let those be arbitrary. So those were just brain states used to do some kind of computation related to one task or another. Obviously, if you know which tasks are being done, you can define your states more appropriately. So there's, I think it's University of California. They have a bunch of researchers that have been doing this type of stuff for a long time. They tend to keep brain states a little bit loosely defined, where if you look at Peter Ashwin at Exeter, he has a number of papers where the brain states have kind of more concrete examples. So one example from the California school would be chunking. So the cognitive processes used in chunking information together, like we do in AI as well. And there we know which kind of cognitive structures are involved, but you're not going down to the level of neurons. Well, another example would be modeling binocular rivalry. So how one eye competes with the other one, kind of puts in more work to adjust for the weaknesses of the other eye. I can't remember exactly how that forms a heteroclinic network off the top of my head, but this dynamic was modeled. And there it's the brain states were defined at the level of neurons, right? Because we know exactly which kind of cognitive processes are firing for which feature of that process we're interested in.
And someone's going to look at the system and go, this is a state, this is a state.
Yeah. Generally very abstract concepts, yeah. These ones, again, are quite well defined, I'd say, yeah.
Any other questions? Okay, let's thanks Dr. Gray for such a nice presentation. So as this was our last presentation of today's session, so now on the behalf of our organizing committee, I would like to ask Professor Gang for a closing remark. Like Professor Shibu mentioned yesterday. Yes.
Thank you, Ali. Yeah, I suppose this this conference was also hosted in Stellenbosch like 2 years ago. Yeah.
Yes.
Yeah. So it's a very interesting selection of topics, and half of the topics I can't follow. But I think like each one, if we can forge collaborations, so there's a lot of interesting topics. Like the last one, so we have lots of like rock, paper, scissors type of games. And of course, if you consider each node, there is a species. And each species has its population dynamics. And they have kind of computational hierarchies. And from that, you can construct the ecological network. So I think there's lots of interesting things. And I don't know what's the plan. So we are trying to have some overall discussions on potential collaborations, research ideas, and Jessica, do you have some plans, ideas? What are the overarching themes emerged? I think today's overall is the applied maths, machine learning type of topics. Yeah. So anyone would like to give some suggestions?
Yeah, maybe
what kind of interesting review articles we're going to write together?
Yeah.
Especially for day one. Let's summarize.
Yes, has something to announce.
So, okay. I mean, sorry I wasn't here the first day.
Yeah.
Thank you everyone to be here. So we were discussing about this workshop on May when I was here with Professor Moyo. And actually it was a discussion we had at the end of the previous 2 years ago workshop. It was like, okay, I met Abdul, I met Ali or Sachin, and we present what we do, but I know what he does, I know what he does, I know what I do. So at the end, it's like, okay, we're happy between us. So the concept was somehow to try to extend it, and so to have Kang team, I mean, to have other people from other group, machine learning. So to see if we can move to that direction, or if we can use tools from that direction, and vice versa, if you can use tools from our direction and from our approach. I understand that now, I mean, to think that and to start making groups, it will be difficult, impossible. But we can go back, and sometimes ideas are going in a moment that we don't think. I mean, when we are working, when we wake up in 2 weeks, maybe we realize something that Jessica present and say, I know that, I want to do something like that. I can use this, so let's connect it. So it was a great opportunity to collaborate, to meet everyone, to know what we can do. And something that will be nice is we didn't organize it and to have proceedings, I mean, event. But maybe we can organize a set of a review article, a big discussion, or some groups between them. Then maybe we can force them and submit it to Africa Mathematica, not as a special issue, but as normal articles, and just to mention the workshop here that they established here. So you are happy. So that's it on my side. You want me to say more? No.
Yeah, thank you. Thank you, Professor Andronikos. Now, now I would like to invite Professor Kara for final remarks. Please, Professor Kara.
This guy is all the work. It was very insane. That's funny. So I think all of you heard the story that when we had the first in the series, he did most of the work then too. That time he was in Pakistan. And that time he was supposed to attend this conference in Stellenbosch University as a protea. And then he got his visa the day after the conference started. So the chief organizer, the guy who did almost all the work, did not arrive. So this time you came months before.
Got better.
So we always say, at least the Lord had paid him back by saying, you have a postdoc in Stellenbosch. Because it's dream to be in Stellenbosch. So you've done a lot of work, and thank you. You know, it's basically been all your work.
Thank you so much.
When you say organizing committee, really the committee was largely you. So thank you very much. And we hope that we can continue this tradition or these activities going to the future, a year's time, 2 years' time. So let's keep it going via this activity, via a proceedings, if we can organize something. Let's keep it going. And the nice thing about, as you said, it was a variety of topics and so on, and there was communication, and that's what it's about, right? Collaboration, communication, networking. And the interesting thing was the number of young people that gave talks and so on. It really was nice. That's another tradition we can keep on. Thank you very much.
Thank you very much once again to all the participants and to all the speakers. And now you are free. So
maybe you can tell them just one little story about this man. So he gets a visa the day after the conference. Then it's like getting it down the next January. This time you get the visa before, but the airline in Pakistan prevents him from getting onto the plane. But and then finally, again, it becomes in August of last year.
I guess.
And then he arrived at the airport in Johannesburg, and they want to know from him. So he made it almost. I did 2 visas.
Unused.
So even when he got the visa, it was almost a problem. He was panicking at the airport because
yes. And
this one is, it's like next year we have at end of June we have a resource modeling conference at the same venue, and of course everyone is more than welcome. And in terms of publications, it's really so publications is very difficult to say let's work together and have a publication. Yeah? But editors of quite a number of journals. So we have a number of special issues ongoing. So one is at advances in complex systems. And currently we are calling for a special topic, mathematics of living systems. And there are also some other journals, ecological complexity, bulletin for mathematical biology, and some, yeah, so there are lots of journals to accommodate this type of interdisciplinary research. And I think the most meaningful one is you have to forge a connection, a network, to really sit down to work with someone. And because in the conference, we have a very short time to interact. And when I know your research, I can see there is a huge potential and for lots of type discussions and so on. Fortunately, we are based at Stellenbosch, so we can interact. But if you're not from Stellenbosch, please interact with colleagues that we found they have very interesting research. Yeah. And if you want to get to know each other, then through Ali, and maybe if you contact Ali.
Yeah.
Yeah.
I will write a formal email regarding the article submission. Thank you so much. Thank you so much.